ಇದು ಯೂಟ್ಯೂಬ್ ಲಿಂಕ್ ಇದೆ.
ಆಯ್ತು ಸರ್, ಆಯ್ತು ಸರ್.
Sir, I'm sending to your mail ID, sir. I'm sending right now, right away I'm sending. Sir, I sent the mail, sir. I already sent the mail. Hello. Sir, it has come, sir. Hello, sir. Okay. Okay. Yes, sir. I'll talk to them. Medha, you have to let Professor Prasad in, our director in. It must be asking you, right?
What is this login ID, sir?
Professor Prasad.
Okay,
Director
okay.
Science. You are able to invite him?
He has not yet requesting, sir.
You know, he is requesting already. He called me twice.
Sir, Ganguly sir had already is in the meeting, sir.
Yes, sir. Yes. Professor Ganguly is around. Hi, good morning. Professor Prasad, he is requesting.
Okay, sir.
Now, I think some expert should join you, I think.
Yes, sir. He's joining, sir. Prasad sir is joining, sir.
No, we're not able to see him on screen. So some expert should join you here. Okay, now Professor,
Yes,
Professor Prasad, good morning.
Yeah, good morning. Can you listen to me? Can you hear me?
Yes, sir. Yes, sir.
Okay, yeah. I am not able to hear you. Can somebody speak?
Sir, am I audible, sir, now?
No, madam, I am not able to hear you. 1 minute. Let me join again. Maybe there is some problem.
No.
I'll just
No,
join
no,
again.
Sir, please unmute yourself, sir. It is.
Now it is unmuted. Now we can hear you, sir. I think
Yes, sir,
all
we
of us
can
were
hear you.
muted, so we could not even speak. I think he has disconnected again. He's trying to reconnect.
Yeah,
Sir, he
can
has
you
joined,
speak
sir.
now?
Yes. We can see you, sir. Good morning, Dr. Prasad. Can you hear us? He is now unmuted. I think we cannot hear him.
Can you hear me now?
Yes, sir.
Yes.
Okay. Yeah, I am also able to hear you. Yeah. I think, yeah, let us start maybe.
Sir. Sir, shall I begin, sir?
Yeah, please.
Yes, sir. Uh, all that disturbances, I'm so sorry. So, good morning, ladies and gentlemen. Professor R.B.N. Prasad, Chairman, RSC Local Section Deccan, Principal of our institution, PC Jabin Science College, Dr. L.D. Horkeri, sir. Dr. H.S.S. Ramakrishna Matte, Scientist, Center for Nano and Soft Matter Sciences, Bengaluru. Dr. C.V. Magat, Scientist, CENS, Bengaluru. All the faculty, students of PC Jabin Science College, Hubballi, and all the participants from all over the country. I welcome you all to this one-day national level seminar on functional nano and soft materials, fundamentals and applications, organized by Royal Society of Chemistry, Local Section Deccan in association with School of Physical Sciences, PC Jabin Science College, Hubballi. We are indeed very honored to work with Royal Society of Chemistry Local Section Deccan. Dr. R.B.N. Prasad is the chairman of Royal Society of Chemistry. He continues to serve in the field of education and research through RSC. He was the chief scientist and the head of Center for Lipid Research at CSIR, Indian Institute of Chemical Technology, Hyderabad. He has over 250 research publications, 20 chapters in books, and 85 Indian and overseas patents. The active role played by the RSC local section Deccan in the field of chemistry and education and encouraging the student community is commendable. Now I request our Honorable Professor R.B.N. Prasad, Chairman, RSC Local Section Deccan, to give opening remarks and let the audience know about RSC.
You are muted, Dr.
No,
Yalamagat.
sir.
No, Dr. Yalamagat is trying to speak something. I don't know. I can't hear him.
Achha.
I think he has to be unmuted. Yeah.
Hello, can you hear me now?
Yes,
We
sir.
can hear you.
Yeah. Good morning, everybody. My sincere apologies for whatever has happened. Professor, our chairman seems trying to get in, but you should allow him. He is trying since 5 minutes. That's what he said to me.
No, it looks like
You
there
should
is
allow
also
him.
there is also an issue of limit being reached. I think that's what once I got the message saying that the meeting has reached its limits in terms of number of participants. So he is, maybe that is what one thing he might be. So one of you probably have to log out and then again.
Yes, sir. Yes, sir. Thank you so much, sir. Thank you so much for the suggestion. we'll take it. I request our Vice Chairman, Professor Pintu Ganguly, to say a few words about RSC, our activities.
I think let me do the inauguration and then when we have Professor Prasad, we can ask him to say a few words. Good morning, everybody. Good morning to our RSC colleagues. Very good morning to Dr. Prasad and faculty and students of KC Jabin College. I think it's indeed a great occasion to have a national level seminar and have our top scientists and teachers talking to students about very interesting subjects. I've been also myself attending and learning many things about liquid crystals and all. So we are surely going to have very good 3-hour session of learning. Now about RSC, now Royal Society of Chemistry was established in 1841. It's more than 180-year-old organization. It's an organization of professional chemists. Basically, the idea is to foster chemical excellence, is to bring together scientists, bring together collaborators, and enable excellence in chemistry. And they have been doing it for the last almost 180 years across different parts of the world. RSC has sections, or RSC has their divisions in almost 175 countries. And in India, RSC has been present for a number of years. In 2014, RSC set up their own office in Bangalore. From there, again, the local Deccan section does very similar thing as RSC UK does, is to bring together scientists, collaborate. We conduct national level seminars, we conduct poster competitions. We also carry out a lot of teachers training program. One of the very important aspects of learning is to have the rightly trained teachers. So we do conduct a lot of training for teachers, training for students, and we have a very good team of colleagues in RSC who has been trying to reach out to students and doing their bit in improving the learning in chemistry. Having said that, RSC also is into publishing. RSC has a lot of very important journals that they publish. It's a not-for-profit organization. It has membership opportunities for college students, for scientists, for very senior scientists, and some of the honorary fellowship of RSC is a very coveted or very sought after and very recognized, or it's a great recognition to have. Like very recently, we had Dr. Gagan Kant being honored with Fellow of Royal Society. It's a very prestigious recognition. So that's what RSC does globally, and in India, as we mentioned, we have 5 sections. Deccan section is one where we are part of it. So with that, I will wish that we have a great session today, and all the best for the next year, and good luck to all of you. Thank you. So now we can go to the next session. I think we are already a little late, so we will start with the technical session. Madam, you can.
Yes, sir. Thank you so much, Ganguly, sir.
Yeah.
So, I request our principal to say a few words about our institution, sir. Thank you.
And thanks to the principal and your faculty for giving us this opportunity. It's a great thing. So, yeah.
I would like to thank our principal here. I request Shri Seth Sandhi, Assistant Professor, Department of Electronics, to introduce our Honorable Professor BLV Prasad sir.
Good morning to everybody. It is my great honor and pleasure to introduce today's national level seminar on functional nano and soft materials, fundamentals and application. Keynote addressee, Professor Dr. B.L.V. Prasad. Professor Dr. B.L.V. Prasad is the Director of Center for Nano and Soft Matter Sciences, Bangalore, who is also working as Senior Principal Scientist, Physical and Material Science Chemistry Division of National Chemical Laboratory, CSIR, NCL, Pune. He had his schooling and his early education in Vijayawada, Andhra State. Later, he moved to Hyderabad Central University, from where he obtained a Master of Science and PhD degree in chemistry. After two postdoctoral stints, one at Tokyo Institute of Technology and second at Kansas State University, he joined NCL in 2003 and continuing there at present. His group is actively working in the general area of material synthesis and in particular nanoparticle and nanoscale materials. He published more than 125 papers in international peer-reviewed journals and has 8 international patents to his credit. He was invited as visiting professor by different universities in many countries, including Japan, USA, UK, France, and Germany.
Thank you so much, Sandy sir. Now the session which we are waiting since the morning, I request our Professor BLV Prasad sir to address this gathering and address the audience in his technical session titled Dress to Function, Nanoparticle Synthesis, Surface Modification and Application. Prasad sir, please sir.
Yeah, okay. Thank you very much. Am I audible?
Yes, sir.
Yes, sir.
Yeah. Let me, first of all, thanks to the RSC local section Deccan. Thanks to Professor RBN Prasad, Professor Pintu Ganguly, and the principal of PC Jabin College for giving me this opportunity to talk to you. This is, I think, my second time to talk to the students here. So it's always a challenge. But anyway, like, let me see what best I can do. And I will start straight away. Can you enable me to share my screen? I need to be enabled. You need to make me host or something like that. Right now it says disabled.
Yeah, please
Just a
allow
moment,
Professor. Yeah, please,
yes,
Professor,
sir.
allow.
Yes.
Yeah.
Yes. Okay. So just a moment, sir. I'm doing it, sir.
Yeah, sure.
Sir, now, sir.
ಅದೇ ಅವ್ರ ಹೋಸ್ಟ್ ಯಾರು ಮಾಡಿದ್ದೀನಿ ಹೋಸ್ಟ್ ನೀನಾದಿಲ್ಲ ಇದೆ ಅದಲ್ಲ
Hello, participant to share screen.
ಈಗ ಯಾರು
Now it should be possible, I think, because now I can also share my screen. I think it should be possible now.
Yes, sir. It is possible to share screen, sir.
Earlier, for a good period of time, I was also struggling. So now it should be possible, I think.
Sir. But I guess
Prasad,
sir.
Yeah, somehow I think he has also got unmuted, got disconnected, it appears. Yeah, now I can share my screen, so you should be also able to do it. We just wait for a few minutes, I think.
Sir. Waiting for Prasad, sir.
I don't know, he may be again struggling to join in because the Zoom link says that it has exceeded the number of participants.
He is joining, sir, now.
Okay, good.
Again, I think
We can
my video is not being allowed. It says host has stopped it.
We can see you. I think we can.
Are you able to see me?
We can hear you.
No, sir.
We can hear you, but
we can hear you, sir.
No, but you need to again allow this.
Sir, please on your camera, sir.
Yeah, I did that. It says, host You cannot start your video because the host has stopped it. So you need to allow me that. Okay. Otherwise, I mean, it's okay. We can probably go ahead without the video also. You just check once. Otherwise, we'll start without the
Yes,
video.
sir. Yes, sir. No participants.
No.
So now, sir.
Yeah.
Yes, we can see.
Thank
Yes.
you. Okay, I think let us start, before another technical
Yes,
thing
sir.
comes up. So, good morning, everyone, all the students. Sorry for all this, late delay and all those things. So I will start straight away by sharing my screen. I hope you are able to see the screen now.
Yes, sir. It is
Yes.
visible, sir.
Yeah, and also, let me take it to the full screen mode. Yeah, are you able to see it in the full screen mode?
Yes, sir.
Okay, yeah. So let us start this session. Let us see how good we can do. First of all, compliments and congratulations to all of us, all of you and all of us, that we are celebrating this Ajatika Amrit Mahotsav in this year, which will be culminating into 75th years, completing of 75th years of 75 years of independence of India in August 2022. So compliments to all of us and all of you for that. Okay. So today, what I'm going to do is basically as I said, I have already talked to you. So maybe you might be feeling again, this fellow has come again to talk to us, and then kind of, especially the students. But these days, more movies come with sequels, right? So you don't not only stop with one movie, you make another movie, you make another movie, you make another movie, like that. So this is my talk is almost like that. So I already gave the talk. I'm repeating probably the talk, but probably with a little bit more dose of masala or whatever you want to call that way. So please bear with me in that manner. And today, and my title of the talk is basically Dress to Function, and this is nanoparticle synthesis, surface modification and application. And why did I choose this title? This title is kind of inspired. I got inspired by this movie. I'm sure most of you see movies. There is a famous movie which has actually been made several times with the same title, and it's called Dress to Kill. Of course, here we are not going to kill anyone, but we are basically making some material to be functional, and I will elaborate on that. What do I mean by this functional materials? Okay, so I'll come to that little later. Obviously, the topic of today is especially my topic, and I think even Dr. Matte and probably Dr. Magat will also elaborate on this little bit later, is about nanomaterials to certain extent. And of course, Dr. Magat will also talk about soft materials. Okay. And when it comes to nano, which nano we should worry about, right? You hear a lot of nanos these days. There is a nano SIM, there is a nano car, there is a nano edge laptop, there is a nano phone maybe. So all these things, are we talking about these nano? And what is the difference between that nano and the nano that we are talking about? The nano that on these cars and then nano SIM, all those things that are telling you is basically a meaning. They're trying to convey you a meaning that what they are talking about is something small, right? So that is what they are trying to convey. But when it comes to science, when we are talking about our own topic, and when we are talking about science and technology, what we mean by nano? What we mean by nano is basically a prefix to a unit, right? The prefix nano means 10 power minus 9. Okay, so this is our meaning. As I said, the other meaning is something small, but our meaning is 10 power minus 9. 10 power minus 9 what? Right? 10 power minus 9 seconds, 10 power 9 minus 9 meters, 10 power minus 9 grams. Which of these three things we should be really concentrating or putting more our emphasis on when we say nano science and technology? And the answer is, this is no brainer, no big brainer. The answer is obviously nanometer. Okay, but the more important thing is that why is nanometer so important when we are not so much excited about nanosecond, we are not so much excited about nanogram. I probably might have told you already this, but still it is better to recap some of these things to complete the story, right? So the nanometer, when it is compared to with nanosecond and nanogram, has something very different connotation or very different, weightage to it, like a very different emphasis to it. Okay, what is that? When we say nanosecond, right? So now we are combining these two terms. As I said, in the popular literature or in the popular talks, when we say nano, means something small and something special. Okay, that's why people call it as a nano car, people call it as a nano sim. It is special, right? So this something small and something special, and with this nanometer or nanosecond. So how do we combine that? So is nanosecond something special when we talk about nanosecond? So the answer is, actually I would argue that it is not. The reason being, in the time scale, nano is not really special, or nano is not really small. What is small in the time scale? The small in the time scale could be a femtosecond, because that is how when you are making a chemical bond, the time it takes to make a chemical bond is roughly a femtosecond, right? And if you are studying the processes of making this bond or making this bond, you need these femtosecond lasers. Or these days, even one step ahead, people have even made attosecond lasers, pulse lasers with an attosecond pulse. What is attosecond? An attosecond is 10 power minus 18 seconds, right? Whereas nanosecond is 10 power minus 9 seconds. So the attosecond is 9 orders of magnitude smaller than nano. An attosecond is 9 orders of magnitude smaller than nano. Therefore, in the time regime, the nanosecond is not really very small. What is small? What can be considered small at this point of time? Because in time domain, you can actually go up to 0. There is something called time 0. T is equal to 0, right? So T is equal to 0, and anything like that, it could be an octosecond, it could be a jeptosecond, it could be an attosecond. Anything larger than 0 is some time. So like in principle, nano is not really the smallest time that you can achieve. Okay, so that you should remember. Then let us go to the weight scale, right? And when you are going to the weight scale, but don't worry about some numbers here, they don't make much of a sense now, right? So in the weight scale, again, you are talking about something special. If you want to make something special, so here generally I ask this question of how many molecules of water will be there in 18 nanograms of water? 18 nanograms of water, how many molecules of water will be there? Why do I ask this question? Why do I put this number of 18? It is very obvious again. 18 grams of water or 18 milliliters number of waters, because 18 grams of water means 1 mole of water, right? So it will contain 1 Avogadro number of molecules, that is 6.023 into 10 power 23 molecules, right? Now if you want to weigh or measure 18 nanograms of water, so you have to simply multiply that with 10 power minus 9 Avogadro number, that is 6 into 10 power 23. Don't worry about 0.22 or 0.223. 6 into 10 power 23 multiplied by 10 power minus 9. Then what you will get? You will get 10 power 14. 10 power 14 molecules of water. They are by no means small volume. Okay. In fact, if you really measure a droplet of water which contains 10 power 14 molecules of water, the water will behave just like bulk water. Whatever this water behaves like, it will behave just like the same thing, right? There is no special property or characteristic that will be associated with that water, right? It will just behave like water, okay, like bulk water, what we call as bulk water. So there is nothing special. If you want to really have some special water displaying special properties or special characteristics, you know how many molecules of water you need to have? You may need to have 100 molecules of water. If you really take 100 molecules of water, you know how much volume of that water will be? That volume, the water volume that will be with 100 molecules of water will be roughly a jeptoliter. A jeptoliter of water. Jepto is 10 power minus 21, which is 12 orders of magnitude smaller than nano. So again, in this weight scale, nano doesn't seem to be very small, because it will have 10 power 14 roughly. If all the elements are molecules, it will be roughly the same, 14, 15, 13, like that. It will be so many number of molecules, and these are not small numbers. Okay, so what I am again trying to say is, in the weight scale, nanogram may not be very small, and a material that weighs a nanogram may not show any interesting properties or characteristics. Therefore, we are not much interested in that. But when it comes to length scale, something very interesting happens. What is that something very interesting happens? Again, nanometer is 10 power minus 9 meters, right? That we all know. So what is 10 power minus 10 meters? 1 order of magnitude smaller than nano. 10 power minus 10 meters. We popularly call it as an angstrom, right? It is 10 power minus 8 centimeters or 10 power minus 10 meters. Okay. So 10 power 10 meters minus 10 meters, an angstrom, is very special to us, especially to the chemistry students. Why is it so special? Because the atoms, molecules, the bond lengths, everything that we otherwise know or talk about is in the size range of an angstrom. Okay, so an atom, the radius of most of the atoms are roughly in an angstrom range. Okay, so therefore, if you assemble few atoms, if you assemble few molecules, right, the size of that entity that has few atoms, like 100 atoms, 1000 atoms, right, that will be the size of that entity having 100 to 1000 atoms will be interested in nanometer scale objects, right? The reason is that there will be only few molecules, there will be only few atoms, and these few atoms, molecules, the entities that are containing these few molecules, few atoms, will display very interesting properties. I will elaborate on that when we are going further. So in that length scale, nanometer is very important or very special. Okay, because given to you as an atom or a molecule or whatever it is, right? So you don't have to really make that. Periodic elements are there, and then all the elements, and then you can combine them, the molecules will make, etc., etc. But you can really make, combining those molecules and atoms that are already existing, combining them, you can really make a new entity with different properties, and that entity, the size of that entity will be a nanometer. That is why nanometer is an extremely important unit in the length scale. A nano is a very important unit in the length scale, not in the time scale or the weight scale. Therefore, I really like this statement, which says that a nanometer is a magical point on the length scale. This is what a famous scientist said about that. Okay, so now let us go further. Right, so nanomaterials display very interesting properties, right? So one of them can be the melting point of the properties, materials changes, right, when they become nanoscale objects, right? The melting points changes. So this is unusual. We don't really expect melting points to change. Generally, when you do an experiment in the laboratory and you purify a material, your teacher will ask, okay, how do you test your purity? Very simple, you go and measure the melting point, and if the melting point matches with the reported value, then you are sure that your material is very pure. But now what we are saying is that melting point is also dependent on the size, right? Your material is this small, this small, this small. That can vary, or that can determine the melting points, especially at the nanoscale. Because once you become little larger, then the melting point, here you can see the graph here, the melting point is not changing when for large particles. Whether you take 200 nanometers or 100 nanometers, the melting point is almost the same, right? Exactly, almost about the same. But when you comes to very small particles, then the melting point of the material starts changing. This is very interesting, right? Also interesting is that the optical properties of the materials change drastically, right? Nothing is more exemplified than this particular example, where these are gold nanoparticles dispersed in a solvent, right? Gold nanoparticles dispersed in a solvent, and you can see the beautiful colors displayed, which is actually made in the laboratory intentionally by a famous scientist called Michael Faraday. And in fact, Michael Faraday was really inspired by this particular cup called Lycurgus cup, which was actually made in 4th century AD, right? So today we are in 200. Jackie Tarannum, she raised the hand. Is there any issue? Are you able to listen to me?
Yes, sir, you're audible, sir. No issue, sir.
Okay. So, this basically, this Lycurgus cup was made, somewhere around 400 AD, and you can see that there are 2 cups being displayed, but there are no 2 cups. This is only 1 cup. One of the cup is, one of the image was taken when the light was shown. It is a reflected light. The other one is a transmitted light, where the light was put in the center of the cup and the light came through the glass, right? Whether the light is reflected by the cup or transmitted through the cup, the color of the cup appears different, right? So Faraday was very inspired by this and then wanted to know, and finally what he could figure out that this is containing some nanomaterials. Of course, he did not know the term nano. He called it as finely divided metal, but he could sense that there is something special about the material which is extremely small. So he made these nanoparticles intentionally, as I said, not knowing that they are nanoparticles. He made these particles intentionally in a solvent, and they indeed displayed these kind of beautiful colors. And then now people make all kinds of other varieties and other colors also, using not just gold, other materials, combination of materials, etc., as displayed by this. We also now understand why these noble metals especially display these different colors at nanoscale. This is due to a phenomenon called surface plasmon resonance, or localized surface plasmon resonance, that is only coming into effect when the material in the nanometer scale, right? Nanometer size object of now noble metals display these beautiful properties. And what is more important, or what is more exciting, is that these properties are size dependent, which means that a 5 nanometer particle and a 100 nanometer particle display different colors. This is again very exciting. Size dependent, properties changing, right? As I said about melting point, here also the optical properties are changing based on the size. Not only dependent on the size, they also are dependent on the shape also. So all these things the size, shape, all these dependencies and properties being displayed by the same material just based on the size or shape is really, really exciting. Again, another example is the semiconducting nanoparticles, our nanocrystals, which are also called quantum dots, especially if the semiconductors and nanoparticles are below a certain size regime, right? So due to again the same material, what you are seeing in this in these sample vials is the same material. The material has not changed. It is basically cadmium selenide, right, of different sizes, and these different sizes are emitting different colors due to a phenomenon called band gap engineering, right? I'm not going through all these details, right? So maybe Dr. Matte will cover some of these topics. So this is exciting, that the same material, just based on the size, is showing different properties, is what is exciting. That's what I want you to understand and and appreciate. Okay. So, and there are interesting characteristics that are bestowed on materials due to these nanostructures, right? Not just nanoparticles, but even if the material surfaces have nanostructures, then also there are some interesting properties. For example, let me stop the pointer. One minute. Yeah. Now you can see this is a nanostructure present on a lotus leaf, and what this is called lotus leaf effect. Again, Dr. Matte will cover some of these aspects, and this is one aspect. The other one is what is called rose petal effect. So this, you can see the difference here. In the case of the lotus leaf, the droplets are running off from the surface, but they are in the shape of a droplet, or a spherical shape, right? Whereas on the rose petal, they're also in the shape of a spherical bead or a droplet, but still they're stuck to the surface, right? So this is all due to the nanostructuring that is present on these surfaces. And as I said, Dr. Matte will cover, but what is exciting now, we also understand why it happens. This is basically the lotus leaf. This is the rose petal. We also now are able to recreate these things in the laboratory. For example, you can see here a glass slide on which we have put some nano coating, and you can see that it is forming like a droplet. It is not spreading. On a normal glass slide, what will happen if you put a droplet? It will just spread. Here it is not spreading. It is basically forming, remaining like a bead and then jumping. You can see how easily it can be. If you just blow some air, it will just jump off. So interesting to create all these surfaces, and there are some interesting technical applications to this. One of the most simplest application that can probably be coming off these hydrophobic surfaces is basically creating non-stick cookware that is not using any Teflon. I'm sure you all know about non-stick tawa that is that you are probably using in the kitchen, but that is containing a material called Teflon. And we don't want to really eat these chemicals into our body. So what we can now make is, without any surface coating, if you make the structure in what is called a hierarchical micro nano structure, if you can modify the surface of your tawa, you can get super hydrophobicity, as it is called. So this can be a very exciting application that you can think of. So this is another interesting application. I find it very interesting. I hope the video plays and also the audio. If the audio doesn't play, also don't worry about it, but please watch the video very carefully. I think the audio is not playing, but what you can watch is that somebody fired a bullet towards this hero, and the bullet has recoated. It has come back. Again, let me play that video. See it. Watch it carefully. So the bullet is coming now. You can see it here. It has hit our hero and went back and basically killed the police inspector, whatever. So it is, it looks very silly to us. But now I will show you one more video. This is more realistic. That is a cinematic video. This is a more realistic video. Here you can see somebody has fired a bullet at a cloth, nylon cloth, right? So what happened? Obviously, it has pierced the cloth and made a hole. Here you can see this nylon cloth is now filled with silica nanoparticles, and what is happening to the bullet you can see. Let me play this video again. Here it is a normal cloth. The bullet has gone through the cloth, and here it is a cloth that is kind of reinforced with silica nanoparticles, and here the bullet has gone back, right? So these kinds of things are now being tested in the laboratory, and these things have very important implications or applications in the area of personal protection, like our soldiers wear very heavy bulletproof vests, etc. So if this kind of a technology comes into market, maybe they can wear like a shirt, very lightweight, but yet it can be bulletproof. This can be very interesting and important for future applications. The last kind of a popular slide I will show, and then go to the particular science that I want to talk about, is about fire retardancy. Here you can see somebody is trying to put fire to a normal cloth, and you see how fast the fire is spreading. And this is this is very again very important because I am sure you must have heard about fire accidents happening to the hospitals in many places, and people dying, especially in ICUs where people cannot move, etc. But here you can see the cloth is now reinforced with nanoparticles, and you can see the fire is not really spreading. How much ever you heat, it is charring, but there is no fire. The material is not catching fire, right? So such things are possible now, and therefore, you can really save a lot of lives if we make the bed sheets, curtains, etc., with this, in the hospitals, especially using these fire retardant materials. Okay, so let me stop on this popular talk now and then go to real science, right? So what is real science here? I'm not going, I told you about importance of nanomaterials, some important properties, etc. But today I'm not really going to talk about nanoparticles. What I'm going to talk about is what is called surface functionalized nanoparticles. What are these? As I said, so this is the nanoparticle. You can see a spherical object here. That could be the core of the nanomaterials. And these nanoparticles will have important properties like I showed you, right? Optical properties, semiconducting properties showing colors, and fire retardancy, bulletproof vests, etc., etc. But I'm not going to again talk about them. What I'm talking about is what is called surface functionalized nanoparticles. What is the difference? So if you take a nanoparticle and so there is a coating present on the surface of this nanoparticle. So that coating is called surface functionalization, right? So what is that coating made up of, right? If you remove the core of the nanoparticle, what is this coating made up of? I'm sure most of you are chemistry students and therefore you can really appreciate what are these. These are nothing but organic molecules, right? Simple organic molecules that we otherwise use routinely in our laboratory called primary amines, thiols, carboxylic acids, tetraalkyl ammonium bromides. These are the things that we are going to, these are our, topic of our interest, or topic of our discussion today, right? So what I'm trying to say, nanoparticles are important, but surface is the key. Why should you pay so much of attention to the surface, right? So why to bother about a surface? Again, I would like to give all these things through analogy because it is easy to explain through analogy. There are two figures being shown here, two photographs shown here, and two legends attached to those photographs, and everybody agrees that this is a photograph of a beggar, this is a photograph of a rich man, and if I want you to guess who is this person, you would immediately, some of you might immediately guess this is a person called Sonu Nigam, very famous singer, Bollywood singer, and probably actor, whatever, right? So what is more interesting to you to know probably is that this person is also Sonu Nigam. You may or may not know it, but he himself did a very interesting experiment. What he did is, on one fine day morning, he wore this kind of a disguise and then sat on a pavement on Mumbai and then started singing with his harmonium and started begging, and nobody cared. Nobody cared really for Sonu Nigam. But the same evening, he gave a concert in an auditorium and with a big hoardings, etc. Sonu Nigam, live show, like etc., and then put a ticket of 1,000 rupees. Here he is begging for 1 rupee, 0.5 rupee, whatever it is, and then singing freely, more or less. Nobody cared. But here he is asking for demanding. He is demanding 1,000 rupees. Unless you pay 1,000 rupees, you cannot come. But people were still crowding. Here, nobody cared. Here, everybody cared. What is the difference between this? Sonu Nigam is Sonu Nigam. The song he probably is singing here and here is same. What is the difference? It is the surface, right? The way he is looking is different, right? So surface is important, right? And so many of our things, right? So I want to go, highlight that particular aspect. And if you don't believe me, you can look at this article. So this guy Sonu Nigam sings on Mumbai streets, goes unnoticed, right? Nobody cares unless he himself declares that I am Sonu Nigam, right? So unless that, nobody cares, right? So today we are going to talk about how surface is important in the area of nanomaterials also, or nanoscience also, right? In that sense, so this is basically that's why my title talk, the talk of the title is basically the title of the talk is basically dressed to function, right? So we are basically now making the nanoparticles and dressing them, putting a dress on their surface, or putting a surface functionalization on the surface, if you want to talk about in a scientific way, right? So we also need to put the dress in an appropriate or a suitable way. What do I mean by this suitable dress, right? So here you can take an example. So if I were talking to you in live, I would on your stage or in your college, I would ask you a question: is this an appropriate or a suitable dress? This particular person has jumped into snow, and what is he wearing? You can see what is he wearing, right? So, and this particular person has put on very beautiful, very formal coat, suit, tie, etc., but it started raining, and he forgot the most important dress, or the most important accessory that is needed for him to be saved from the rain, right? And that particular thing is nothing but an umbrella or an overcoat, right? So obviously this particular thing is not suitable dress, or not an appropriate dress for the kind of functions they want to do, right? So what would be? Put an appropriate dress. You need to put an overcoat, or something that protects you from rain. Or if you are going into snow, you put another suitable dress that protects you from the snow, right? So today I am going to distinguish these two kinds of things. What will be a suitable dress depending on the application of the nanomaterials. So these nanoparticles can be used for many applications. I'm going to highlight 2 applications and then say, how do you make nanoparticles suitable for that application using these molecules, organic molecules. So therefore, organic molecules are going to play a very important role when you talk about nanoparticles being used for an application. That's what I'm going to highlight today, right? So what are those 2 applications that I'm going to highlight? So you can see many applications that are possible with nanotechnology, but 2 of the applications that I'm going to highlight is this medicine and drug and energy, right? So again, to highlight my discussion, let me play a video here. Again, so I need to probably go back and then, yeah. I hope you can see the video. Again, I think the audio is not coming through. I'm very sorry for that. So what is being told here is that how to make future integrated circuits are basically the electronics for future, right? So right now these electronics or integrated circuits are being made by what is called photolithography or electron lithography, etc., etc. But what these people are now trying to do is to use printing, not lithography, but printing. The printers, these are obviously high technology printers, but still the concept is almost the same. You make an ink and then print whatever you want. This has huge potential for future applications, because this can be done much faster as compared to the photolithography that is being practiced today, and can be made at much larger scale, right? You can do it in much larger scale, and you can also do it on flexible substrates. Right now, whatever photolithography you are doing, you may not be able to do it on flexible substrates, but for future phones and other electronic gadgets which you want to fold it and keep it in your pocket. So this printing technology is going to be huge, right? So you can see like your inkjet printer, everything is being printed, right? So you basically draw a structure and the same thing can be printed on a circuit, right? This is extremely going to be important in the future applications. So here for us, what is the key? The ink that can be used to print, right? So that is basically creating the active material for this integrated circuit. So ink is the key, and that ink will definitely contain nanoparticles. How to make that ink, we will talk about a little while later. The other application that I'm going to talk about, again, if the audio doesn't play, don't worry about it. I will explain it. Is about nanoparticles being used for drug delivery applications, right? So here you can see several cells. These are basically mammalian cells, and here you will see 2 cells. I will probably stop in between the videos and then try to explain you different aspects of this particular thing. Here you can see 2 cells, right? So this is basically a normal cell. This is a cancerous cell. Obviously here one more. So you don't want this cancerous cell to be present in any patient's body. You want to kill them. But right now, if you give a drug, the drug does not distinguish between a normal cell and a cancerous cell. It kills everything on this slide, right? You don't want to do that. What you want to do, you want to give a drug in such a way, like a missile, that can go and hit the target, only the target, nothing else, right? So very kind of a guided missile. So how do you do that? So you basically make nanoparticles, because nanoparticles can enter into the cells, because nanoparticles are smaller than these cells, so they can enter into the cells, but they need to enter specifically only into the cancerous cell. So to do that, what you will do is you will put some targeting moiety. So this moiety is present on the surface of the nanoparticle, know where to go. They will not go to the normal cell. They will only go to the cancerous cell, tag onto the surface of that cancerous cell using the specific interactions between some of the moieties that are present on the cancerous cell, which are not present on the normal cell. So there is a specific interaction. Because of the specific interaction, this drug-loaded nanoparticles go only to that particular cancerous cell. They are ingested, they are taken into the cell, and then once they are into the cell, they can be even sent to the nucleus, as you can see here what is happening. So once they go to the nucleus, the nanoparticle kind of disintegrates and then releases the drug that is present inside. You will see that in the video in a little while. So now the the drug loaded nanoparticles are going into the nucleus of the cell. Now you can see the cytoplasm, and then now you can see the the nanoparticle is slowly being digested. And once the nanoparticle gets digested, it starts releasing the drug. You can see that now the red dots here are the drug. So that drug is getting released. Once the drug gets released, basically it kills the cell, right? Now you can see only this cancerous cell is getting killed or disintegrated, whereas the normal cell, nothing happens because the drug has not gone into it. Drugs are highly cytotoxic, right? So that is why it is a very specific targeted drug delivery applications. So just to highlight, what are the important characteristics for these two applications: nanoparticles for printed electronics, nanoparticles for drug delivery applications. You can see, right? See this for both of them, the dispersions in for the printed electronics, preferably the dispersion should be non-polar solvents, right? So, and they should provide good electrical conductivity. They should be easy post-printing processability and prevent aggregation in the ink form. And for drug delivery applications, the dispersion should be in polar solvents, because our body is containing water, which is a polar solvent, right? So there should be precise control, because you cannot say I made nanoparticles of 5 nanometers and 100 nanometers, because then the FDA or cannot do that. You need to precisely tell me whether you have a 5 nanometer particle or a 100 nanometer particle. You cannot say I will have something whatever I want. They will have control on that. So there should be payload flexibility. You should be able to put whether it's a hydrophilic drug or a hydrophobic drug. You should be able to put it in, right? Easy surface modification. I will come to that. Again, this also needs to avoid aggregation and toxicity. The nanomaterials itself should not be toxic, because you are giving it into the body, and the drug should be able to highly bioavailable, which means that so whatever drug is present inside, it should be easily accessible to the cell material inside the body, right? So these are the important characteristics for these two applications. So let us come to how do we make these nanoparticles. So you can make them in two approaches. One is what is called the top-down approach. The other one is bottom-up approach. Basically, the English word meaning itself tells you about something. So in the top-down approach, you start with the bulk material, grind it, right? Make it smaller and smaller. If you see the old movie, if you saw the old movie Sholay, the Dharmendra says checky piecing. So the top-down approach is nothing but checky piecing, right? So you basically take the bulk material, grind it, and then instead of using a checky, here you will use a scientific equipment called ball milling. So the ball mills basically, they basically mill the material from bulk size to the way of making nanoparticles, or the what is called the top-down approach of the bottom-up approach of the nanoparticle. Here, what we do is we start with something smaller than nano. And as I told in the beginning of the talk, something smaller than nano is basically the atoms or molecules, because they are in the angstrom scale. So you basically make the atoms or molecules, assemble them, make them into nanoscale objects, and then stop the reaction, the chemical reaction. And that's it. If you do that, you know how to make nanoparticles in a laboratory. Just to highlight that aspect, I'll again show you one video. Let me see whether it is playing. Sorry about that. Okay. So you can see the video here. Here, my student is basically trying to make gold nanoparticles. So this is similar to any other metal. We make gold because it is a little more stable than some of the other nanoparticles. Some of the others might catch fire. It could be security hazard. So we don't want to do that. Gold is stable, so we make gold nanoparticles. Other than that, I don't have any particular obsession to gold. Maybe my wife has, but I don't have anything like that. Okay, but like it is more stable to show you. That is why we are showing it. See, you can see here they have taken a gold precursor, a gold salt, diluted it. This is extremely important to make. As I said, the reaction has to be stopped when all the material becomes a nanoscale object, right? That is why you need to play with concentration here, and then add a reducing agent, and that's it, right? Because in the gold salt, gold is present in the oxidized form. Gold ions are present. That means gold is not having the sufficient number of electrons. Gold, the stable oxidation state, one of the stable oxidation state is +3. So the gold salt is available as AuCl3 or HAuCl4, where the gold ion is present in +3 oxidation state. You supply electrons. How do you supply electrons? You reduce them. You add a reducing agent. This reducing agent transfers the electrons to the gold ions. So the gold ions becomes gold atoms. These gold atoms will come together, and when they come together, they become nanoscale objects. But after that, there is no more gold atoms or the salt that is present. All of it has been consumed. Therefore, they cannot grow much larger. That is basically what you do by controlling the concentration of the precursor solution you take. And this color being displayed here is an indication that gold nanoparticles have formed. And this was actually done, as I said, like by Michael Faraday in 1857, and somebody, a person called Turkovich and his group have mastered this technique and then made the nanoparticles using not a very fancy reducing agent, but a very routine reducing agent called trisodium citrate, and that was done in 1951. So when we know how to make nanoparticles in 1950s or 1850s, why is that we are talking about nanoscience and technology today? Why was there such a gap, right? The problem with these nanoparticles, though it is very easy to make them, is that they are not very stable, right? What do I mean by stable? These nanoparticles are available as a dispersion in a solvent because they are covered by a layer of charges, right? In fact, a double layer of charges, right? So again, don't worry about the details. So if you really take a TEM image, you make a dispersion, put it on what is called an electron microscope grid, and then look at an image, they do look like separate particles. You can see discs here. These are not discs. These are spherical particles, because you are taking an electron microscope image, which converts a three-dimensional object into a two-dimensional image. You are seeing like a disc, but these are basically spherical objects, right? So you can see very spherical, separated particles here. No problem. But the problem comes when you want to do something with them, right? So as a dispersion, they are stable. You can do something in the laboratory. You can do an electron microscope image. You can study their optical properties. But beyond that, if you want to do anything, these are not very stable, right? By the way, the trisodium citrate molecules structure is shown here, right? So these are not very stable. These are almost like colloidal dispersions. What are the famous colloidal dispersions? Milk, blood, milk, right? It is a colloidal dispersion. If you add some salt, what will happen? If you add salt to the nanoparticles, by the way, so here is a question. So we have already made the nanoparticles. Can we start using them from electronic applications or drug delivery applications? I have told you already. The problem with that nanoparticles is that, so anything you want to do them, they start aggregating and lose their nano characteristic, right? So they will no longer remain as nanoparticles. They will aggregate and become larger particles. Here is one example shown here. This is just like you add salt to the milk and then it basically becomes cheese or paneer, whatever you want to call, right? So it is an irreversible process, right? Like in the milk case. So once these nanoparticles aggregate, it is very difficult to bring them back into a dispersed state. This particular state of nanoparticles is called dispersed state. This particular state of nanoparticles is an aggregated state, right? It is very difficult to, it is easy to come this way, but it's very difficult to go back. It is not possible, right? Therefore, you cannot use these nanoparticles for many applications. And people realize that. And in that sense, these nanoparticles, so as I said, for both these applications, for printed applications and drug delivery applications, the dispersion should be stable. For printed electronics, the dispersion should be in non-polar solvents. For drug delivery applications, the nanoparticles should be in polar solvents, right? But stable dispersions. Both of them require stable dispersions. But what we made nanoparticles, but these are not stable. In that sense, these nanoparticles can be compared to a newborn baby, right? Because these nanoparticles are dispersible in polar solvents. They are not useful for electronic applications, but these are dispersible in polar solvents, but not stable against stimuli. They're not good for drug delivery applications. So in that sense, these nanoparticles are just like newborn baby, right? A newborn baby is kind of naked. All of us were born like that, right? I don't think anybody in this audience were born with cloths wearing, right? Wearing the cloths, right? So you are born naked. What a mother or a nurse in the hospital does as soon as the baby is born? Will they go out and then display the baby saying that, Bahubali is born? They will not do that, right? What will they do? Immediately the baby is, kind of protected from environmental hazards and all those things by a nice cozy towel or whatever it is, like a blanket, whatever people have handy. So they will basically protect the baby. So likewise, these nanoparticles are now naked. They don't have any cover. They're only protected by a layer of charges. So what people thought is, can we protect the nanoparticles? By the way, so after that, we start wearing, the dress doesn't just remain as a protective layer. It has, it assumes a lot of important things later on in the life as we grow, right? So for different occasions, I will come back to that later, right? So here, these nanoparticles, these are kind of your naked nanoparticles. These are the capped nanoparticles. By the way, give me another 10-15 minutes. I think we started a little late. So I will end in maybe 10-15 minutes or so. Okay. So this is what we are doing now. We are protecting the nanoparticles using a layer of organic molecules, just like we protected the baby using a bed sheet or a towel, right? So what is this? And this particular cartoon shows the molecule like this, but these are molecules like, as I said, alkane thiols, alkylamines, etc. I'll explain that in a little bit later. But you can use any molecule? No. This molecule also should have some particular characteristics. What are the characteristics that this particular molecule should possess? One of them, that there should be a functional group that allows, because most of the nanoparticles are inorganic in nature, metals and other systems, etc. So you need to have what is called a bond between an inorganic surface and an organic molecule. So there is an inorganic organic hybrid interface that is present. So you need to enable that. So you need to have a particular capping moiety that allows you to anchor this molecule to the nanoparticle surface. That is important. Then you need to have an alkyl chain, preferably an alkyl chain, but other possibilities are also there. Possible, I will cover that later, right? So these type of systems are called what are called monolayer protected nanoparticles, right? Because there is at least one layer of organic molecule present on the surface of the nanoparticle. So what is the advantage of that? Now you can actually make larger materials, so larger volume fractions or weight fractions. And these materials, I will show you again, these are very stable against external stimuli. They don't aggregate like the charge stabilized nanoparticles that they did in the previous slide that I have shown. And there are also other advantages. I will not cover that. So the first reported preparation of these monolayer protected nanoparticles was done by a group from University of Liverpool in UK, David Schifrin and Matthias Brust. And they did this nanoparticle synthesis in a slightly different way than that was shown in the video earlier. What did they do? They also took metal precursor, because they are making metal nanoparticles, but they phase transferred these metal ions. They did not allow the metal ions to be, or the metal salt to be in water. They took the metal salt into an organic non-polar solvent, right? Using a surfactant, tetraalkyl ammonium bromide, like I told you, right? So they phase transferred that. In the organic solvent, this basically means non-polar solvent. Water and this non-polar solvent are not miscible, but you are adding a surfactant. So they will make what is called a reverse micelle, inverse micelle, microemulsion, whatever it is. What does it do? This is having small, tiny water droplets protected by these surfactant molecules. And inside these small water droplets, which are in the micron scale or sometimes even in the nano scale, this small water droplet has those metal ions present. Right? So now the metal ions are confined to these extremely small water droplets, which are present in a sea of oil, basically, right? So now you add your reducing agent. Earlier, we took the metal salt in water, directly added reducing agent. But now what we did, we took the metal salt, phase transferred it into a non-polar solvent using a surfactant, and then made a microemulsion or a small reverse micelle, and into that we added a reducing agent. And apart from adding reducing agent, what these people also have done, added another organic molecule or a capping agent or a ligand, whatever you want to call. In this case, they added dodecane thiol, a thiol molecule, SH, containing an R group containing 12 carbon atoms, C12H25, right? C12H25SH. You can see that here. So that is the molecule that he used, right? So this dodecane thiol molecule, what it did is, as soon as the gold nanoparticles got formed, it went and then sat on the surface of these gold nanoparticles, because thiol, or the sulfur atom, likes to make a bond, make a bond with the gold, right? So the surface gold atoms made a bond with this thiol or a sulfur atom, and therefore there was a layer of organic molecules present. So why was it done? What was the advantage of doing this? The advantage of doing that is that now you can precipitate the nanoparticles. Now it is not aggregation. You can precipitate the nanoparticles and redisperse them, right? So, you know, if you add a bad solvent to any material that is dissolved in a good solvent, so like, you know, maybe like, you know, benzoic acid or whatever it is, if you add a bad solvent, it makes a precipitate. And you remove all the solvents and again add a good solvent, it again becomes a solution. Similar way, you basically make a dispersion of nanoparticles, precipitate them and redisperse them. So this is the advantage, right? You know, redisperse them any number of times. Now you can purify the nanoparticles. Now you can separate the nanoparticles. Now you can do a lot of these things. Now this monolayer protected nanoparticles with a small alterations are good for your electronic applications, right? So this is why it took some time for us to realize the application potential of the nanoparticles, because we did not know how to handle them. Now we know how to handle them. It is very easy to handle them, right? So we also know a lot more about the ligands that needs to be used. We now characterize or categorize these ligands into 3 different classes. We call them as L-type ligands, we call them as X-type ligands, and Z-type ligands. X-type ligands are those that make a covalent bond with there is an inorganic, this is the inorganic surface, this is organic molecule, so there is a covalent bond being formed. This is an L-type ligand, which basically makes a bond using the lone pair of electrons. Adarsh Gowda Patil, okay, yeah, so he was coming on video. So anyway, this particular thing, this is a lone pair, this is a vacant orbital on the ligand, and this is a lone pair present on the nanoparticle surface. So this can also make bond. So, and these are the different types of ligands. And L-type is basically primary amines, phosphines, phosphine oxides, carboxylic acid. X-type are carboxylates. There is a difference. This is a carboxylic acid, this is a carboxylate, or thiolate, or chloride, OH, etc. These are the different categorizations of the ligands. So, and with this, we can do many more things. I don't think I will have time to do that. So let me cover. So now, I already told you about how to make nanoparticles with a stable coating on the surface that can be used for, as I said, printed up electronic applications. Now let us come back to the drug delivery applications. For this, the dress has to be different. You cannot use the same nanoparticles, because those nanoparticles, you can make these nanoparticles, no problem. But for this, these nanoparticles have to be dispersed in water. These are not dispersible. Right now, these nanoparticles, as I told you, these are the type of molecules that you are putting on the nanoparticle surface. These nanoparticles are dispersible in non-polar solvents, right? But they are not dispersible in water. And for drug delivery applications, what did we say? We needed to have the nanoparticles in water. How do you make these nanoparticles in water, dispersible in water? So for that, you need to simply modify this particular end of the molecule, right? So if you modify this particular end, put a hydrophilic moiety. The previous one was a hydrophobic moiety, CH2, 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 CH3. This is hydrophobic moiety. If you simply modify it and make a hydrophilic moiety, then these nanoparticles will be dispersible in water, right? So these things can be used for applications, like drug delivery applications. 1 or 2 examples I will show and then close it, right? So we do something like that in our group. And then what we do is, there are different ways of making these water dispersions of nanoparticles. One is that you make first non-polar dispersions of nanoparticles, and then again exchange the surface ligand with a molecule containing these kind of dual functional groups. If you notice, this particular molecule has 2 functional groups. One functional group that attaches to the nanoparticle surface, that one functional group that is basically associated with the solvent molecules like water, etc. Right? So this can make a lot of hydrogen bonds with water. Therefore, these nanoparticles are dispersible in water. So you need to have dual functional molecule. So you make a nanoparticle with with a molecule containing one functional group, but then you exchange it, right? with a molecule containing dual functional groups. And then you can make water dispersions of nanoparticles. But we said, can we make the nanoparticles in one go? Water dispersions of nanoparticles directly from a metal salt. So to do that, we designed a particular molecule. Now you come to very important aspect. You need to design molecules. You can design molecules for suitable for an application. Here we designed this molecule called sulforolipid. So if you notice, the sulforolipid is nothing but what is called a modified oleic acid. Oleic acid is a very famous molecule, very easily available. So what we do is we take oleic acid, take it, add some yeast. This is like fermentation. You do while baking, right? Cakes and other things, you add some yeast. Similar yeast you can add. This particular one of the best yeast is a species called Candida bombicola. So you add some yeast and glucose, and then in the lab, my students say, you just do this. Yeast does the rest. You don't have to do anything. What is yeast doing? It is basically converting this oleic acid into a sulforolipid molecules. But unfortunately, this is a bioorganic transformation. So yeast is not a very good chemist like us, right? It is not having good experimental hands. So what it does is it gives a mixture of products. It doesn't give one product. It gives a mixture of products. But we know how to convert that mixture of products into one product by converting it into using a procedure called a base hydrolysis. So once you do that, this is a lactonic form, this is an acidic form with a lot of acylation, etc., etc. Don't worry about that. But just note that this is a mixture. This mixture is converted into a pure form, into an acidic form sulforolipid. By the way, why are these molecules called sulforolipids? Because this dimeric glucose is called sulforose, right? So basically sugars are known as these O's: galactose, glucose, fructose, etc., etc. So this is molecule called sulforose, and therefore these molecules are called sulforolipids, right? So again, Pintu, Prasad, I will answer the questions if you have anything. Just give me a few more minutes and then I will be done. Okay. So I have seen a raised hand here. So using these sulforolipids, we could make silver nanoparticles. And very interestingly, because these sugar molecules are reducing sugars, we did not even add any extra reducing agent. We simply added sulforolipid into a metal salt called silver nitrate, and then added a little bit of base and then heated it. This is like a tolerance reagent or a silver mirror test that you do. But what is beauty here is that, so these are the as prepared particles, with whatever the procedure you make. But we precipitated them out and redispersed them. Now in water, I told you about charge stabilized colloids. These could not be redispersed, but here we could redisperse them very easily into water. And then using this, now what we have done, we have made protected nanoparticles. These are dispersible in water. And then can we test them for an application? Now we know how to make suitable dresses for the nanoparticles. So we made one suitable dress. That suitable dress is to make them dispersible in water for a particular application. So we need to make another dress for the nanoparticle suitable for another application. Let me show you how to do that, right? So we now made nanoparticles with suitable dresses. Are they ready to function, right? So we tested them because these are silver nanoparticles. We tested them for what is called their antibacterial activities. And again, I don't want to go through all the details, but believe me, they were very good antibacterial activity. Silver by itself is very good, but these were even better because even the sulforolipid capping that is present is also, that molecule is also antibiotic, right? So therefore, the combination of silver plus that particular molecule gave us enhanced antibacterial activity, especially against what is called gram-negative bacteria, which is otherwise little difficult to kill, right? So this is one thing. So now we made one type of dress that makes the nanoparticles dispersible in water. But will it be good enough for all the applications? Yes, it is good for antibacterial applications. But can it be good for cancer treatment? No, because there is no drug available on the surface. The sulforolipid is good for killing bacteria, but it will not be good to kill the cancerous cell, right? So how do you do that? So we need to modify the dress again, right? Here, the dress assumes greater significance. The dress in the on the surface of the nanoparticle. So just to highlight that point, I have shown again 3 figures here, and then if I put this particular legend, you will laugh at me. How do you know that is this a bridegroom? You will now say no, he cannot be a bridegroom unless you know what is involved in when you get married, right? So it is very difficult. It's a different ball game altogether. But anyway, the answer is that so what you need to have is basically, so a bridegroom is like this. But who told you that this is a bridegroom, right? So you know that associated with the dress, there is a function, right? So in the actual life, right? For a function, there is an associated dress. So this particular person is going to fight a war. He cannot go with this dress. No, he'll be killed in no time. This particular person is going to do a mountaineering. Again, he cannot go with the dress or with this dress. No use. He has to go with an appropriate dress. Similarly, if you want to make nanoparticles for applications, functions and applications, here cancer treatment, you need to appropriately dress the nanoparticle. To show you an example, we made again gold nanoparticles capped by a molecule called Galen gum. It's a natural gum available. It is approved by FDA and other drug control agencies for consumption by human beings. Therefore, we wanted to coat the nanoparticles with this Galen gum, and we made it. The details I am not showing. So once we made the Galen gum coated nanoparticles, what we did is we coated these nanoparticles with a very highly cytotoxic drug called doxorubicin hydrochloride, right? Why was this possible, or how was this possible? Because this Galen gum had a moiety called glucuronic acid, a negatively charged surface, right? So using the electrostatic interaction between the glucuronic acid and the doxorubicin hydrochloride, which is having a NH2HCl kind of a moiety. So these two things allowed us to load the drug on the surface of these nanoparticles. Once we loaded this drug on the surface of the nanoparticles, we tested them against some cancerous cell lines, especially brain tumor cell lines. And we got very good activity, right? So we got very good activity. This is cell lines only. We did not study still in animal models, but believe me, again, they showed very good activity. There is some challenge, especially when you talk about brain tumors, because the drug has to cross what is called blood-brain barrier. And this Galen gum, which is nothing but a sugar, right? As I told you, it is allowed for human consumption. It adds a little bit thickening agent and like a sweet kind of an flavor. Therefore, this is the blood-brain. It could cross the blood-brain barrier because the blood-brain barrier thought it is a sugar, and it allowed it basically. So we thought that is the strategy we want to use, and then we could indeed show that these are good activity, right? So the last example I want to show you is you may not be happy or satisfied with just adding one particular surface modification. We have added one surface modification in one example, sophrolipids. In the second example, we added two functional moieties, that is Galen gum, which allowed you to cross the blood-brain barrier, and a drug, right? Now we want to add even one more, that selective targeting, because in the previous example also there was no selectivity. Any cell it basically enters into, it can enter into. But we wanted to now add selectivity, right? So why is it important? Again, to highlight that, I want to show you, what is important of these multifunctional addresses on the surface. Here, this particular example, you can see, these two people want to get married, and these days it is fashionable to marry in a different kind of, under different challenges. Marriage itself is a big challenge, but these people want to have additional challenges. So what are they doing? They are skydiving and getting married. So these two people are getting like that, it's okay. But poor fellow, this fellow is carrying a Bible and reading for them, basically, right? But luckily, all of them are wearing a parachute, right? So this saves them. So here, in the area of nanomaterials also, we wanted to do a multifunctionality or adapt a multifunctionality or add a multifunctionality to the nanoparticle. So what did we do? We actually made BSA coated nanoparticles. BSA is bovine serum albumin, or the equivalent of humans is HSA, human serum albumin. So why is this important? See, what is cancer? Cancer is nothing but uncontrolled division of cells, right? So some cells are getting divided, they're not getting killed, but they're getting divided, right? So when something is getting divided so fast in an uncontrollable fashion or growing, this division is nothing but growing in number, basically, right? When something is growing faster, right, uncontrollably, it will need food for that, right? It will need some energy for that, right? So serum albumins are the energy for the cells to divide. So what we thought is, let us coat the nanoparticles with a drug and serum albumins. Now what will happen? The serum albumins will do two things. One, they will stabilize the nanoparticles. The second, the cells, which are the cancerous cells especially, which are dividing very fast, they will think this serum albumin as a food and take the nanoparticles inside. And along with the nanoparticles, there is a drug also loaded on the nanoparticles that also goes inside. But since the cancer cells take the nanoparticles more because they are dividing much faster, right? Remember, both the cells are taking, but the normal cells are taking the food at a slower pace, whereas the cancerous cells are taking the food at a much faster pace. Therefore, more of the food is being taken by the cancer cell. Therefore, more drug is going into the cancer cell as compared to the normal cell. So we did all that. Like, so again, don't worry about the particular details, but this particular cell slide is important. Here you can see these are normal cells, normal fibroblast cells, NH3T3. And when we fed these nanoparticles loaded with the drug, to just show you this example, this is not the drug, this is a dye loaded on the nanoparticle, Texas red. So you can see that there is not much of a dye that has been taken up by these normal cells. But when it comes to cancerous cell, most of the drug and dye has been taken inside by these cancerous cells. Mind you, both of these figures, images were taken at the same time point. So once we show that, like, so we could show that, this is a preferential uptake that is happening. So more or less, that's what I wanted to show you today. So I showed you how to make suitable dresses to the nanoparticles, functionalized nanoparticles. Like you want to make organic dispersions, you need to select a particular type of dress. If you want to make water dispersions, you need to select another type of dress. And actually, interesting thing is that you can not only have one type of dress, you can have multiple dresses on the surface. Like I am wearing today, one shirt and then another jacket. You can do a lot of things on the nanoparticle surface also, depending on the type of applications that you are envisioning for these nanoparticles, or this type of applications that you want to use these nanoparticles for. Right. So in that way, so like whatever we are doing as a nanoscientist is very similar to a tailor. You may not like it, but I am happy with it. Like, so we are nothing but a little bit of tailors, nano tailors, if you want to call that way. So they make very suitable dresses for people, whereas we make nanoparticles with a suitable application potential. Right. So this is what we make, either, as I said, organic dispersions or water dispersions, of surface functionalities that can be used for many very interesting applications. So this is what we make. And nanoscience, this particular dress making is probably creative and beautiful. Nanoscience is also very creative but very useful also, right? Thank you very much for your attention. Maybe I have taken probably 5-10 minutes more, little more than that, but I wanted to convey a message, so sorry for that. I will be happy to take any questions if you have. Thank you very much once again. Maybe I will stop sharing and then
So all that wait was worth it. So I request the audience, if they have any queries or if they have any questions, they are open to discuss with Professor Prasad sir.
I think Professor Pintu Ganguly wanted to say something. Sir, you are muted. You are muted, Dr. Ganguly.
So please, you can raise the hand there, sir. I'll just unmute you, sir.
No, he's not. I think again, he is not allowed. Yeah. You can put your something in the chat box also. I will be able to read it. If it is, yeah.
The questions can be asked in the chat box also. Okay, then I would like to thank Professor Prasad, BLB Prasad sir, Director, CENS Bengaluru, for his wonderful talk indeed on dress to function nanoparticle synthesis, surface modification and applications. So his way of presenting the science of small particles in comparing with the day-to-day life examples was fascinating, I can say. So I would like to extend my thanks to him, and I thank the RSC local section Deccan for giving us an opportunity to hear the talk of Prasad sir. Yes, sir. Ganguly sir, you can unmute yourself and.
So I also put my message. So I wanted to thank Professor Prasad to say that his sequel is as interesting as his first edition, and we hope to see more sequels of Dress to Kill. A very interesting talk and very well connected. And I think the great tailoring that you are doing will surely lead us to great drugs and very useful chemistry, sir. Thank you, sir.
Thank you very much. Yeah, I appreciate. Thank you very much. Yeah.
Yes, sir. So thank you, Prasad sir.
Yeah, sure. Yeah, maybe you can move ahead. Yeah.
Sir. Okay, so now I would like to request Srimati Sheila Gandhar to introduce Dr. C.V. Magat to the audience.
Good afternoon, everyone. Myself, Sheila Gandhar, representing from the Department of Physics. Dr. C.V. Magat sir obtained PhD degree from Karnataka University and carried out postdoctoral research at the Department of Organic Chemistry, Indian Institute of Science, Bengaluru, and Applied Chemistry, National, and he got the postdoctoral degree from the Applied Chemistry National University, Taiwan, since from 1997. He has been a scientist at the Center for Nano and Soft Matter Sciences, Bengaluru. His work focuses on soft matter, nanomaterials, and nanosoft composites and other closely related systems. His journal research publications are over 200 with H index of 37 and over 4,000 citations. He has 11 national and international patents in his credit. He has presented over 300 invited talks and written reviews and textbooks. He has been the recipient of the state government's national and international awards and fellowships, Japanese government's JST award in 2000 and JSPS award in 2002 and 2003. Fellowship, Government of Karnataka has given Sir C.V. Raman Young Scientist Award in 2005, the Royal Society London Visiting Fellowship in 2007, MRSI Medal in 2019, FRSC Fellowship of Royal Society of Chemistry Award from the Society of Chemistry London, UK in 2019, CRSI Medal in 2021, Executive Member of RSC, Royal Society of Chemistry, Deccan Station. He has been figured among the top 2% scientists in a global list compiled by the prestigious Stanford University. Okay, with this brief introduction, I will conclude myself. Thank you.
Now I request Magat sir to start with the technical sessions. Sir, please. Hello, sir. I'm unmuting, sir. I'm unmuting it, sir. ಅಲ್ಲ ಸಿದ್ದು ಅಣ್ಣ ಬಾಯ್ಲಿ ಪ್ಲೀಸ್ 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 ಬಾಯ್ಲಿ 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 ಹಾಂ ಇದು ಮೀಟಿಂಗ್ ಸ್ಟಾಪ್ ಆಯ್ತಲ್ಲ ಒಮ್ಮೆಗೆ ಹಾಂ ಮಾಡಿದ್ವಲ್ಲ ಎಂಟು ಮಾಡಿ ಸ್ಟಾರ್ಟ್ ಮಾಡ್ಬೋದಂತೆ ಮತ್ತೆ ಎಂಟು ಮಾಡಿ ಸ್ಟಾರ್ಟ್ ಮಾಡ್ಬೋದಂತೆ ಮತ್ತೆ ಇಲ್ಲ ಇದೇ ನಿಂತಲ್ಲ ಸರ್ ಒಮ್ಮೆ ಕಾಲ್ ಮಾಡಿ ಸರ್ ಕಂಪ್ಯೂಟರ್ ಫುಲ್ ಇದಾಗಿದೆ ಸರ್ ನೆನಪಾಯ್ತು ಸ್ಕ್ರೀನ್ ಇಂಟರ್ನೆಟ್ ಅಲ್ಲ ಸರ್ ಕಂಪ್ಯೂಟರ್ ಹೌದಾ ಹೌದು ಓಕೆ ಸರ್ ಈಗ ಅವರಲ್ಲಿ ಸ್ಕ್ರೀನ್ ಓಪನ್ ಮಾಡ್ಕೊತಾರೆ ಸರ್.
Hello, am I audible now? Hello.
Yes, sir. You are audible, sir.
Yeah. Now it's fine. You are able to see my screen?
Yes, sir. It's visible, sir.
Okay. Good afternoon, each and everyone. Am I audible clearly? Somebody should speak. Am I audible clearly?
You are audible clearly, sir.
My screen can be seen?
Yes, sir.
Yeah. Once again, good afternoon, each and everyone. At the outset, I would like to express my deep sense of gratitude to PC Jabin Science College and Royal Society of Chemistry, local Deccan section, for giving this wonderful opportunity to interact with fellow BSc students and faculty members. I'm especially grateful to Principal PC Jabin Science College and our Chairman, Vice Chairman, Professor Ganguly, Professor Prasad, and other members, Secretary Dr. Radha, everybody for giving me this wonderful opportunity. Well, today, as I mentioned to you, today I'm going to talk to you about one of the fascinating aspects of science. Before I do that, I think you have to unmute. Some background noise is there, you have to unmute. Madam? Madam, hello?
Sir?
You're able to hear me?
Yes, sir. I can hear you, sir.
Yeah, please unmute yourself.
Yeah, yes, sir. Yes, sir.
Yeah. Okay, before I proceed with my actual presentation, I would like to say a few words. I think it's very important to the, especially the students and faculty members, to know where I'm working and the significance of this place. This was established way back in 1991 by great Professor Sivarama Chandrasekhar. Okay, yes, Chandrasekhar is popularly known as SC. And another professor is there, Dr. Subramanian Chandrasekhar, who won the Nobel Prize in 1983. You'll be really pleased to know that Professor Chandrasekhar, who established our organization way back in 1991, in fact, is a nephew, CVR's younger sister's son. I think all of you know Sir C.V. Raman. And another Chandrasekhar, who won the Nobel Prize in 1983, who is astrophysicist, he also is a nephew of Sir C.V. Raman. Now, you can imagine Professor Chandrasekhar's stature. In a sense, he was outstanding physicist. I learned much of the chemistry from Professor Chandrasekhar, although basically he was by practice he was a physicist. They are coming from the same family. I mean, they are coming from, Professor Chandrasekhar is coming from Sir C.V. Raman family. If you look at their nose, they have some kind of identity. See, if I put a peta on top of them, you can see all three, they look alike. So in fact, Professor Chandrasekhar was nominated on 3 occasions for a Nobel Prize. And unfortunately, he demised sometime in 2004. And that's how we really miss him. In fact, he has made a big contribution as far as the science and technology of Indian science and technology is concerned. He is the one who discovered discotic liquid crystals. He is very popular for that discovery. Well, this is our new campus. What I showed was a new old campus. It was in Jharkhand. Now it is a new campus. This is known as now Center for Nano and Soft Matter Sciences. It's a 14 acres of land. It is a beautiful place to work. It is quite away from the city, and we are not perturbed, and we are happily working here. So right from beginning, we have been working on soft materials. Those can be used for LCD technology, liquid crystal display technology. Most of you use, right now you're using mobile phone or you're using your laptop. All of them comprise a small unit, which is the heart of your device, as it's called liquid crystal display. In this center, we are trying to make materials which can be used for liquid crystal display technology or solar cells, for the fabrication of solar cells. Dr. Mate will be talking about solar cells. Here, our solar cells, I mean, the kind of solar cells we are making through liquid crystal is that it's all organic. You use organic molecule to realize what are known as solar cells. We are also focusing on gels. Gels are also used in liquid crystal displays. In your liquid crystal display, these are organic molecules. They are, I mean, more or less, you can say they are of different composition. They have different composition, but they are basically organic compounds. Okay. Now, if I can replace this organic compound with gels, you know what is gel. I did not go into in the detail in the interest of time. Gels can also be, instead of organic molecule, you can also use gels for the LCD fabrication. In recent times, we have been trying to carry out a perfect marriage between nanomaterials and soft matter. Nanomaterials are ultra-fine materials, ultra-fine, very tiny materials, as already Professor Prasad has spoke to you. And they are very, 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 tough, in the sense they are very hard materials. On one end, you have soft materials, and another end, you have nanomaterials. Now, when you try to mix them so as to realize what are known as soft and nano composites, there's a phase separation. There's a serious phase separation problem. Okay, you are taking a hard material, hardest material on the earth, and you are taking very soft material, and you're trying to mix them, they don't get together. There is what is known as phase separation. As Professor Prasad has already mentioned to you, what we are trying to do is we are trying to cap nanomaterials. It could be any metal, it could be derived from any metal. We are trying to cap them with organic molecules capable of showing liquid crystal phases or liquid crystallinity. So now we have nanomaterials or nanoparticles capped with liquid crystals. So you get soft nanocomposites. They not only exhibit the properties of liquid crystals, also they exhibit the property of nanomaterials. Well, right from beginning, we have been focusing on the molecular design, sense, and characterization of naturally synthon-based both conventional and non-conventional liquid crystals. As I mentioned to you, we have been also working on nanomaterials and LC&P composites. And the class of conventional liquid crystals, raw-type molecules, we have been trying to come up with organic molecules. Those can be straight away used in LCD technology. To some extent, we have been very, very successful. On the other hand, we are trying to make molecules for molecules for solar cells or photovoltaic cells. In a sense, we are trying to make the whole, we were trying to make electron-rich, electron-poor, and fluorescent discotic liquid crystals. So all these three combinations can be used to generate solar cells. That I can put in a very simple way. We have been also working on liquid crystals. They are called non-conventional liquid crystals. In particular, they are called oligomeric liquid crystals. You take one liquid crystal, one organic molecule that shows liquid crystal behavior. It has one function. You take another molecule, it has another function. When you combine the two, you have a dimer, and that dimer exhibits the properties of the two entities A and B. So I've been very successful. We have demonstrated that using this, one can make beautiful molecules. Those can beautiful, wonderful compounds that have different functions to perform, and they can be used in different applications. Well, we have been also working on banana-shaped liquid crystals. These, the very interesting aspect of as far as the banana-shaped liquid crystal is concerned, although at the basic level, there is no clarity. Am I audible? Am I audible? Somebody should speak. Am I audible? Yeah. Okay. Thank you. Okay. Although at the basic level there is no molecular clarity, but when they self-organize, okay, they give rise to a structure that has a chirality, and such macroscopic structure can be used for the fabrication of what are known as FLCDs, means ferroelectric liquid crystal displays. And recently, as I mentioned to you, we have been working on soft nanocomposites for different applications. All right. So I'm trying to adjust here. So soft nanocomposites, what we have done, what we are doing, or what we have done is that we have taken, especially we are working on gold and silver. We're trying to take gold nanoparticles, as Professor Prasad already mentioned. He uses organic molecules of different function, but here what I use is organic molecule. They show liquid crystallinity. What is liquid crystallinity? I'll come back to that point. This my talk revolves around that particular topic today. We have been also trying to develop polymers, coordination polymers, and metal organic frameworks for the detection of toxic metal ions, toxic gases, and explosives. And I'm very pleased to let all of you know that we have been able to make few systems, coordination polymers. They have the ability to detect explosives. We have been able to detect as many as 7 different types of explosives using simple chemistry, simple coordination polymers. Now, we have been also trying to address the issue of energy. As most of you know that in the days to come, you will run out of fuel, you will run out of kerosene, you will run out of all kinds of energy sources. So in that case, we are left with only water. You have plenty of water, that to sea water. Now, what we are trying to do is, we are trying to dissociate water, decompose water into its elemental composition. Like when you decompose water, you get hydrogen and oxygen. So oxygen is environment friendly, whereas hydrogen, it can be used as energy source of energy. So we are trying to develop catalyst that dissociates water or splits water. A lot of work has been going on all around the world, including at JNC. Professor C.N. Rao is working a lot on it. He's trying to develop electrocatalysis. So we are also trying to make few catalysts. Those can be used for splitting of water. Now, coming back to my presentation today. Today, I'm going to talk to you about one of the fascinating aspects of science. I think it's a very basic question. What is matter? Matter, I think the answer is very simple. Matter is everything around you, extremely simple. But matter is an object that occupies, as all of you know, matter is an object that occupies a space and has a mass. It can be visible or invisible. For example, whatever you have around you is visible, but air is not visible, but you are breathing. Matter is a very important point to be noted as far as the BSc students and some of the faculties. Is very important to note that matter is made up of atoms or group of atoms and molecules. Yes, we all of us agree. But why do they exist in different forms? That is extremely important question to be answered by people like you who are just in the learning stage. The correlation between the constituent atoms is different. You know, each and every set of matter is made up of some chemical constituents. Now, how they correlate with each other? Now, how they talk to each other, how they associate with each other, that matters a lot. Eventually, because of that, you are getting different states of matter. Well, right from beginning, right from our school days, we have been made aware of the existence of different states of matter: solid, liquid, gas, and plasma. As all of you know, solids, they have their own set of properties. Liquids, they have their own set of properties, gas and plasma. In a sense, you have different states of matter, and these states of matter have different functions or different properties. And as I demonstrate now, solids, they have a certain set of properties, and these properties are exactly contradicting to the properties exhibited by liquids. For example, listen to me carefully, solids, they never flow. Right? But when you come to liquid flow. Please see the opposite character. Solids, they fall, but they never flow. Liquids, they flow, but they never fall. You take any liquid, if you try to pour, they will flow, but they not fall. Okay? There's a continuity. When you take a cup of water, when you try to drop from a height, say 1 meter, there's a continuous fall. There's a flow that it doesn't fall. Okay, so these are the two important properties of a solid and liquid. I shall repeat again: solids never flow, whereas liquid flow. Why does it happen? Why? So you must think why it happens. Now, likewise, gas and plasma. I intended to say that you are aware of the different states of matter, and also very importantly, you are aware of the fact that they exhibit different properties. Why do they exhibit different properties? Well, I shall come to that point a little later with all the technical details. Now, today I'm going to talk to you. I'm going to declare, or I'm going to say that in addition to the existence of different states of matter like solids, liquids, and gas, indeed, there exists another state of matter called liquid crystals. So liquid crystal, I think most of you have heard liquid crystal display. In fact, it is very important point to mention that all of us, not only you and me, anything that exists on the earth and that has a life is all constituted of liquid crystals. Ladies and gentlemen, all of us, all living beings on this earth are composed of n number of liquid crystals. Means you are a bundle of liquid crystal. Okay, our life has started with, say, unicellular systems, then it transformed to bicellular system, tricellular systems, and we are multicellular systems. All of us necessarily comprise, whether it's unicellular system or bicellular system or multicellular system, all of us necessarily comprise what are known as liquid crystals. Liquid crystals is yet another state of matter. I shall repeat, we all living beings which are on this earth, we are all composed of, or we can say that we are a bundle of liquid crystals. In your body, there are n number of liquid crystals. Interesting. Let me explain what exactly it is. Well, now, in addition to the liquid crystal, I'm going to talk about liquid crystals today. In addition to liquid crystals, you do have another state of matter called Bose-Einstein condensate. Ladies and gentlemen, from today onwards, if someone asks you, tell me the different states of matter, then you should start with Bose-Einstein condensate. You should start with Bose-Einstein condensate, then Bose-Einstein condensate, solid, liquid crystal, liquid, gas, and plasma. Well, Now, importantly, I have shown an arrow here. When you come from Bose-Einstein condensate and goes up to the plasma, see what's happening. Energy is increasing. When you talk about Bose-Einstein condensate, they have low energy, and they are, their energy is very, very low. Okay, and then when you talk about solids, so the energy content is little high. And when you talk about when you go from solid to liquid crystal, the energy content is little higher. And then when you go from liquid crystal to liquid, the energy content is higher. Likewise, you can go on. A very important point to be noted that liquid crystal is another state of matter, like other states of matter, like Bose-Einstein condensate, solid, liquid, gas, and plasma. Liquid crystals represent yet another state of matter, and very importantly, they form the basis of our life. Not only your life, it can be anything on the earth. Okay, any living being which is present on this earth, all of them comprise a liquid crystal. I want to reiterate on the point, even it can be unicellular system, amoeba, it can be unicellular system, it has a liquid crystal. So in what way? Let me explain later. And other aspect is that most of us, I think there's no life. I may forget pen and pencil or notebook while coming to the college. I may forget my wife somewhere in the market, but I will not forget my mobile phone. I think all of you agree with me. Well, that's on the latest side, but what I'm trying to say is these days, technology advanced so much. Now we are not unable to live. I mean, it is almost compelled. It appears that government is going to ask, or some organization is going to ask a newly born baby to have a mobile number. So it means that we have been, we are addicted to this mobile phone. So all this mobile phone have a small panel called liquid crystal display. So now we can understand without mobile, I think most of you are through with your studies using mobile phones. I mean, your online classes, how are you listening to me? It's due to mobile phone. So that mobile phone is active only when liquid crystal work on that particular surface. You have two glass slides in the mobile. So they comprise liquid crystals. They are nothing but, please note that liquid crystals are simply organic or metal organic compound. They respond to the applied electrical field. Therefore, you have been able to create images on the screen. Well, in order to understand what are liquid crystals technically, I would like you to recall what is melting, what is evaporation, what is condensation, and what is freezing. All of you know that solid melt into liquid state. Liquid upon further heating goes to evaporation state, and you can come back. A gas upon condensation you get the liquid, and upon freezing you get a solid state. Now, today I told you that upon heating there are some class of organic molecules or metal. They are very simple, extremely simple organic molecule. When you heat them, they do not go to liquid state directly, but they pass through intermediate state. They're called liquid crystal state. Now this has to be changed. What? There are some kind of organic molecules. Upon heating, to begin with, they're solid. Upon heating, they do not straight away go to liquid state, but they pass through fourth state of matter called liquid crystals. All right. Now, in order to understand what are liquid crystals technically, one must note a few important characteristics or properties of solids. As all of you know, or you have been taught, that solids are of two types. One, amorphous, another crystalline. So you have two types of solids, amorphous solids or crystalline solids. Again, crystals can be divided into two classes, isotropic and anisotropic. Now, hereafter, I'll be referring to only anisotropic crystals. I shall repeat, solids, two types. Solids, there are two types of solids, one amorphous, another crystalline type. So crystals are further divided into two, isotropic and anisotropic. Now, I'm referring to only anisotropic crystals here. What do you mean by anisotropic crystals? Okay, overall, let us define what are solids. In solids, atoms or molecules or ions are held rigidly because they possess the positional order, orientation order. They maintain their shape. They do not flow. They cannot be compressed, and they exhibit what is known as birefringence or double refraction. So what do you mean by positional order? Molecules are restricted to occupy a specific site in a given lattice, And orientation order means molecular axes are pointed in the specific direction. It can be either towards you or towards me, or it could be anywhere. Please note, very important point to be noted here is that, please be alert. The important point to be noted is that anisotropic crystals possess position order, orientation order. Therefore, they do not flow. Please note this point. Crystals, anisotropic crystal, they do not flow. I shall repeat, they do not flow, but they show what is known as birefringence. Please note, anisotropic crystals, they do not flow. For that matter, any solid you take. But here I'm talking about anisotropic crystals. Why I'm calling it anisotropic crystals? I'll come back to that point a little later. A crystal which you refer to as anisotropic crystal, it has to show a phenomenon. It has to show a phenomenon that is known as double refraction. That is nothing but birefringence. Okay. Okay. Then what do you mean by birefringence? You know the refraction. Birefringence is nothing but a magnitude of double refraction. What I'm trying to say is you are referring to anisotropic crystals. Anisotropic crystals never flow. That point to be noted. Therefore, they show what is known as double refraction. First, let's try to understand refraction of light. It is the bending of light ray when it travels from one transparent medium to another. You hold a glass of water and fill it with with water, and when you try to put pencil, it appears as pencil is bent. Ladies and gentlemen, as all of you know that it is not the bending of pencil, it is the bending of light. When light travels from one thin medium to thick medium, transparent medium, the pencil appears as if it is bent because of the bending of light. What is double refraction then? Double refraction, it is the bending of light into two different directions when it travels through an anisotropic medium such as crystals. So when an ordinary beam of light is made to pass through, please note this point, when an ordinary beam of light is made to pass through what are known as anisotropic crystal, for example, calcium carbonate, the incident beam of light gets split into two. One is called ordinary beam of light and extraordinary beam of light. Now, interestingly, when you take such a crystal, which is called anisotropic crystal, and it has a very interesting property. When a beam of light passes through this anisotropic crystal, the incident beam of light gets split into two rays. One is called ordinary beam of light, and other one is called extraordinary beam of light. Now you take this crystal and a pencil and put on the top of it. Take a pencil and on the top of which you should put anisotropic crystal. It appears that you have two images. Note that one pencil gives you two images just because I have put a calcium carbonate crystal on the top of it. What does it mean? It means that one image is originating because of the ordinary beam of light. Another image is originating because of the extraordinary beam of light. Now, interestingly, when you rotate the crystal, okay, so the image which originates because of the ordinary beam of light, which follows all the optical laws, remains stationary, whereas the another image which originates because of the extraordinary beam of light rotates with the angle which you rotate. That is quite interesting. If I were to be there personally, I would have shown this one. We have crystals. I can show you this phenomenon. Coming back, two important points to be noted in order to understand what are liquid crystals technically. Two important points to be noted is that we are talking about anisotropic crystals. Anisotropic crystals have some interesting property. First and foremost, they don't flow. They don't flow, but at the same time, they show what is known as double refraction. That is, when an incident beam of light is made to pass through anisotropic crystals such as calcium carbonate, the incident beam of light splits into two. One is called ordinary beam of light and extraordinary beam of light. All right. So if that is the case, let's try to understand how to figure out there is a anisotropy in the crystal. Okay. Now, in our day-to-day life, we use so many plastic items. Okay. When you go to market, or when you try to pack something in your hotel, they give you a plastic bowl, and on top of that you have a plastic cover, and you use plastic bags, transparent plastic bags. It could be Scotch tape. You take any plastic bag which is transparent. All of them can be referred to as anisotropic systems because they show double refraction. Okay. Now, for example, if you take your scale, plastic scale, it shows double refraction, means it is birefringent. So most of the plastic items are birefringent in the sense these plastics are made up of polymers. These are polymers and they are strained. Strained polymers show what is known as double refraction, like those of anisotropic crystal. Strained polymers, they show what is known as double refraction in the sense when an ordinary beam of light is made to pass through your plastic scale, the incident beam gets split into two. One is called ordinary beam of light and extraordinary beam of light. Now the question is, as a BSc student, you must ask me a question, sir, how do I know that my scale is showing double refraction? It's not easy to make out just with the naked eye. You should have what is known as, you should use what are known as polarizers. Okay. How to test a given crystal is birefringent or not? You should use polarizer. Okay. When an ordinary beam of light is made to pass through polarizer, the vibration of light gets confined to a single plane. So this is what is known as plane polarized light, and the vibration of light wave gets into to a single plane. Means here you can see this is unpolarized light. A light wave that is vibrating in more than one plane is referred to as unpolarized light. When such a light is made to pass through a polarizer, I think you most of you heard about polarization of light. When an ordinary beam of light is made to pass through a polarizer, the vibration of light gets confined. I'm talking about only electrical vector. So this is a horizontal polarizer. The vibration of get confined to a single plane, that too in a horizontal way. Now I can have two states. Polarization of light, I can have two states, one vertical state and horizontal state. When an ordinary beam of light is made to pass through vertical polarizer, you have vertical state. Okay, it is called vertical state. When the same thing, if you rotate it by 90 degrees, you have horizontal state. So I can, using polarizer, vertical polarizer and horizontal polarizer, I can derive light of two kinds, one vertical state, another horizontal state. Now, when I take a two polarizer having horizontal orientation, then light comes out. But when I talk about cross polarizer, you take one polarizer which is horizontal, another polarizer which is vertical. If I put them on top of each other, light get extinguished. I think you must answer, you must think why it is happening. Okay, that I don't have time to get into all those details, but what I intend to say is you take one polarizer, it has a horizontal state, and you take another polarizer of vertical state and cross them, light won't emerge. So it is a single polarizer here, two polarizers of the same orientation. You have two polarizers that have opposite orientation. It has a horizontal orientation, it is a vertical orientation. When you put on top of each other, they are called cross polarizer. Between the cross polarizer, light won't emerge. Okay. Now, if I put anisotropic crystal, please note what is happening. Between the two cross polarizer, there was a air is isotropic, light won't come out. But when I put anisotropic crystal, okay, what happens is that light emerges. Now, in place of this, if I put water, light won't come out because our water is isotropic. Between the two cross polarizer, now I'm putting a crystal, anisotropic crystal. Okay, as I mentioned to you, anisotropic crystal are birefringent. I mean, the incident beam of when an ordinary beam of light is made to pass through anisotropic crystal, the incident beam of light gets split into two. One is called ordinary beam of light and extraordinary beam of light. You are seeing this one, this beautiful color, because of the interference of both ordinary and extraordinary beam of light. Extraordinary light doesn't follow any optical laws, therefore it is called extraordinary beam of light. Simply, when you put anisotropic crystal, which doesn't flow, I shall repeat what I'm saying. If you take an anisotropic crystal, which doesn't flow, and put between the two cross polarizer, you'll get to see the color because there's anisotropic. Okay. Now, if I take any plastic item, as I said, you take a scale or plastic item, anything. Now, if you take that plastic item, put it between the two cross polarizer, you will be able to see beautiful color. It is because of the beautiful color, is because of the interference of both ordinary and extraordinary beam of light. Now here I have shown the crystal wherein I have put the crystal between the two cross polarizer. Therefore, you will not be able to see the fluidity. I put a crystal between the two cross polarizer. You are able to see only the color or light, fluidity. Simple. You take anisotropic crystal, put between the two cross polarizer, you get to see light, but there is no fluidity. Okay. Now here two important terms to be noted is that no fluidity but birefringence. No fluidity, birefringence. Now when I go to liquids, now let us try to see what are liquids. Okay. Liquids, in the liquid, molecules are held loosely and they diffuse randomly. Their intramolecular attractive forces make them to held together. They associate with each other through intramolecular attractive forces. In liquids, unlike in solids and liquids, the properties of liquids are exactly opposite. Technically speaking, the properties are exactly opposite. In liquids, in solids, we have position order and orientation order, but in liquids, no position order, no orientation order. They do not maintain their shape, they flow. Please remember, recall, solids never flow, but they show birefringence. But liquids, when you talk about liquids, they flow, but no birefringence. Simply, we should understand crystals, anisotropic crystals, they show birefringence, but they do not flow. Liquids flow, but they don't show birefringence. Okay, now let me quickly go through this slide. Solids, they possess orientation order, position order, birefringent, and no flow. Well, on the other hand, liquids, no position order, no orientation order, not birefringent, and they are fluid and viscous. With this background, let us try to define what are liquid crystals. Let us try to understand what are liquid crystals. Okay. Okay. I think I need to. Am I audible? It is frozen. Hello?
Yes, sir. You are audible.
Yes,
sir.
I'm audible.
Yes, sir.
You are able to see the screen? Something got something has frozen here. I'm not able to move. 1 minute, please.
But your screen is visible, sir.
Okay, fine. Yeah, is visible now?
Yes,
visible.
sir.
You can see the movement of the molecules.
Yes, sir. We can see the movement, sir.
Okay. Now, it's very, very important to note that when you talk about solids, given the fact that in solids, the constituent chemical species are held tightly, rigidly. Therefore, there is no movement at all. Please note that point. But on the contrary, exactly opposite, when you come to liquid, molecules tumble in all possible directions. You simply gulp water, but you understand water molecules will be dancing inside. But when you freeze, when you take it to ice, the molecules, the water molecule will be frozen. But when you come to water, the molecules will be dancing like this inside. So that is how the molecules are associated as far as the solids are concerned. I shall repeat, in solids, molecules have position order and orientation order. Therefore, they show birefringence, but therefore they don't flow. When you talk about liquids, there is no position order, there is no orientation order. Therefore, they do not show birefringence, but most importantly, they flow. Now, when I take a crystalline sample, anisotropic crystal, put between the two cross polarizer, you get to see the color, but there is no fluidity. But when you talk about a liquid, for example, if you take liquid water, put between the two cross polarizer, you will not be able to see the color because there is no birefringence. But there is a fluidity. Here, color, yes, no fluidity. But when you come to liquid, there is no color, but there is a fluidity. Okay. Now, with this background, let us try to understand what are liquid crystals. Anisotropic crystals, no flow, but birefringence is there. When you talk about liquid, there is no birefringence, but there is a fluidity is there. Ladies and gentlemen, God has created, the Almighty has created, the cosmos energy has created a state of matter that shows both the properties. That is, when you put liquid crystal between the two cross polarizer, that not only show the birefringence, but also flows like liquids. Whenever you talk about birefringence, there should not be fluidity. Whenever you talk about fluidity, there should not be birefringence. The examples are anisotropic crystals and water. Now, God has created a state of matter called liquid crystal. it shows the properties of both. That I mean to say, liquid crystal, which represents another state of matter, it flows like liquids. It flows like liquids. At the same time, it shows birefringence like those of crystals. So here is the slide which summarizes whatever I have said so far. Liquid crystals are the intermediate state between the solids and liquids. And I want you to focus, most importantly, focus on how molecules are associating with each other in a given state of matter. Now let's start with solid. In solids, we have orientation order, position order, birefringence, and no flow. Come to liquids, no position order, no orientation order. Sorry, there's no birefringence, and fluids are viscous. Now, ladies and gentlemen, please look at the liquid crystal. Liquid crystals have orientation order. So far, about 53 different liquid crystal phases have been discovered. Okay, all of them, if you want to call a state of matter as liquid crystal, they should show what is known as orientation order. In addition, some of them also have position order. So it may the position order will be either in 1 or 2 dimension. If you go to time, I'm not talking about the cubic phase. And they are liquid crystals. They have orientation order, position order, birefringence, they flow, and viscous. Please note that the first 3 properties are coming from solids. The other 2 properties are coming from the liquid. All right. So that's how the liquid crystal is constituted. Now, given the fact that it comprises the properties of both solids and liquid, therefore they are called liquid crystals, and they are the unique state of matter. Therefore, they're called unique state of matter. I intended to say that. Okay, now if I heat a liquid crystal between the true cross polarizer, what would happen? It should flow, and when it goes to isotropic liquid, it should become dark, right? Because when it goes to liquid, it's a liquid, there is anisotropic isotropic material. Therefore, you have a dark field of view. Please imagine you have a solid substance, you are heating it, it enters into, before it goes to liquid state, it enters into liquid crystal state. In liquid crystal state, what one should be expecting this color, birefringence, the birefringence and mobility. Okay, but when you go to liquid, there is a mobility, but there is no color. So this is what I'm going to show you here. We are able to see the movement. Okay, there seems to be some problem. Let's see, try this. Okay, doesn't matter. Okay, in essence, today I wanted to talk about. Today I wanted to share you the one of the fasting aspect of the science. In particular, I intended to talk to you about liquid crystals. What are liquid crystals? They form the basis of our life. All of you are composed of n number of cells. Each and every cell is covered by liquid crystal in the form of plasma membrane. I shall repeat, all of us are composed of n number of cells. Each and every cell, please note, each and every cell is covered by liquid crystals. What is that? That cell wall, you take any cell if you take of anything, any living being. Living beings have a cell, they are considered of cells. Cell is well protected by liquid crystal. Liquid crystal is nothing, I mean, the cell wall is nothing but liquid crystals. That's what I intended to say. Liquid crystals, they flow like liquid, and they show double refraction like those of anisotropic crystals, and they are optically anisotropic. They possess orientation order and position order. In essence, today I have been able to let you know that there exists another state of matter called liquid crystal. They show the properties of both solids and liquids. They flow like liquids. At the same time, they show a double refraction. Okay, thank you very much. Thank you. Hello, am I audible?
Hello, sir.
Hello. Yeah, thank you very much, madam. Thank you.
Yes, sir. Yes, sir. Yes, sir. Thank you so much, sir. I would like to request the participants to ask any queries either in the chat box or they can raise their hands and I'll unmute them.
I had to hurry up because I have some other work. I had to hurry up. I'm so sorry.
Okay, sir. Okay, sir. Then I would
Okay.
like to thank you for this presentation, sir, and addressing the audience about liquid crystals and soft matter, sir.
Thank you so much, madam, for giving
Thank
this.
you, sir.
Once again,
Thank you.
I would like to express my. I think it's my it is my pleasant duty to thank PG Jabin College. I know that all of you know that I'm from the same side. I'm from Hubballi, and I love to give presentations in either PG Jabin College or Kothambri. Once again, I would like to thank the principal of the college, Madam Yu, and the RSC members for giving me this wonderful opportunity. Thank you very much.
So thank you for giving us an opportunity to host you, sir. Thank you, sir.
Thank you so much.
Thank you, sir. What? I guess Prasad sir, BLV Prasad sir is taking a leave. I would like to thank him on behalf of Jabin College and all the faculty and students for staying with us for so long and giving us a wonderful lecture. Thank you, sir. Magat sir, you can stop the sharing of the screen, sir.
Yes, I'm trying to.
Yes, sir. Yes, sir. Yes.
It has frozen.
Ha. Okay, sir. Okay, sir. Okay. Okay. Moving towards the next session, I would like to request Dr. S.B. Kaujalgi, Associate Professor, Department of Chemistry, PC Jabin Science College, to introduce the resource person for the next session, Dr. Ramkrishna Matte.
Okay. Good afternoon to everyone. I am Dr. S.B. Kaujalgi, Associate Professor in Chemistry. I take this opportunity to introduce Dr. H.S.R. Matte to this one-day national seminar on functional nano and soft materials, fundamentals and applications. I am excited to introduce H.S. Ramakrishna Matte, currently working as a scientist D at Center for Nano and Soft Matter Sciences, Bengaluru. Sir obtained his bachelor's degree from Government College, Rajmundry in 2000 from Andhra Pradesh, master's in 2009, and completed his PhD in 2013 under the guidance of Professor C.N.R. Rao, FRS from Jawaharlal Nehru Center for Advanced Science Research, working on various aspects of nanomaterials. Sir did his postdoc at Northwestern University, USA from 2013 to 2015 under the guidance of Professor Mark C. Hersam and Professor Tobin J. Marks in the area of organic solar cells. Later, he moved to Professor Norbert Koch Group at Humboldt University, Berlin, to work on doping of organic semiconductors. Sir currently working research interests are printed electronics, low dimensional materials, electrochemical sensors, batteries, and organic photovoltaics. Dr. Matte has published more than 50 research articles in reputed international peer-reviewed journals with 6,900 citations, having H index 28. Sir got 3 patents to his credit. His group is actively involved in collaborating with various multinational companies looking for the possibilities of commercializing nanotechnology-based products from laboratory to land. With this brief introduction, here I present Dr. H.S. Ramakrishna Matte sir to this seminar. Thank you all.
Thank you, Dr. S.B. Kaujalgi sir, for introducing our resource person. Now I would like to request Ramakrishna Matte sir to begin with the technical session and address the audience. Sir, I'll unmute you. I'm going to unmute you, sir, now.
Hello. Are you able to hear me?
Yes, sir. Yes, sir.
Okay. I really thank the organizers for giving me the opportunity to interact with the BC Jabin College, Science College. So I'm just trying to share my screen and see whether, let me know whether you're able to see the full screen.
Yes, sir. The screen is visible.
And the slides are moving? Perfect. Perfect. Yeah. So, I mean, before getting into these things, the technical aspects, once again, as I said, thanks the Royal Society of Chemistry and the Royal Local Tech Section for giving this opportunity where I'll be discussing with you for some time, for the next some 20-25 minutes, an overview of next generation or the new generation solar cells. It is a bit difficult for anyone to focus or to deliver the lecture close to 1:30. I clearly understand that aspect of it. So I'll see that I'll not really bother you so much. Of course, it would have been nice if it is a bit early and where I get a chance to discuss in detail. But I'm seeing completely from the listener perspective. If I'm sitting in an audience, I would definitely hate to listen things at this time because somebody grabbing my lunchtime is not something one would appreciate. Yeah, but let's see whether I would convince you in the next 20-25 minutes, definitely not more than that, on what are solar cells and what are the basics that you learned in your college. Like, see, what happens is most of the times, when you learn things in a more abstract way, you may not give any attention to that. Particularly when it's that's the reason people say that one need to learn things by doing experiments. So by doing so, what will happen is you will get the feel for the systems that you're doing, and then learning the concept behind how that experiment is working or why the results are coming in a certain way, and giving a theoretical background to it would be much more effective way of learning or teaching things. So in that context, I was asked to talk about the organizers, particularly Dr. Magat has asked me to comment or discuss about the solar cells, and then he asked me to correlate with respect to nano and 2H. So, and with the expertise or the background that I have, the only thing which I could correlate the nano, and I mean, coming from my background, I'm not saying it in general, the organic solar cells is the one topic where you have a significant amount of nano involved in improving the efficiencies of the devices. But directly getting into organic solar cells would be a bit too much, as it really requires a bit of fundamental understanding on how a solar cell works. And knowing this audience are at best of bachelor's level or the +1 +2. So I thought, okay, let me give a very brief introduction to solar energy and get us try to understand how the electronic structure forms, and then going to the classification of materials, PN junctions. I mean, for the first 4 topics, let me make it clear that I think your teachers will be doing a much better job than me, as they're doing this one for their courses for some time. But I just will try to give you from a device perspective, so that you will have a clarity on how these things would work and how it is relevant when you are fabricating the devices. Because when you talk about the electronic structure or a PN junction, to some extent it will be interesting for sure. But when we know that they have direct relevance to solar cells, you will have a bit more. You will have some kind of affinity for understanding them in detail. So with these things, I'll just go to the technical aspect of it, and then yeah. So one second, somewhere in the close. Yeah. So now, why we are talking about why are we talking about this energy or solar cells? As if you see on this curve, which is on the left hand side, where you are talking about the world population and the energy demand growth. As you can clearly see, the population increases and the world energy consumption also increases. There is nothing great about it to understand, right? Both of them are proportional to each other. But what is alarming is this particular aspect of it. Where the population of the industrialized countries would probably remain the same, probably the developing economies like India and other countries, where the population growth is growth is more. So it means that we will be requiring more energy down the line, because with the more population, more electronic gadgets, and then other aspects, not necessarily the electronic gadgets, but the power consumption and the required for fuel and other things would increase with increase in population. So now it is of important, particularly to in the context of India, to develop resources where we can be self-reliant in this case. And as you know, it is important also to get these things from a strategic perspective. I mean, in the time of war, people may not supply you the ammunition required if you are not self-reliant. In the similar way, in the time of the fuel crisis, there may not be any imports available for country, even if you have money, because they are not ready to export it. So it is critical and imperative for us to be self-reliant in this context. And most of the things which we are currently using are coming from various energy sources, like the majority of them are from non-renewable. But if you get into a renewable energy sources, that would make things much clearer. Like if you see the oil and the gas, the fossil fuels are close to 87%. So we need to contribute to see that we are self-reliant from a non-renewable perspective. And there is also a need for these things as well, for one simple reason, because you'll have other impacts like pollution, climate change, and mining on these aspects. But if you go towards a traditional aspect, like an unconventional or a safer way of getting energy, like the nuclear, hydroelectric, or solar, of course, everything has its own advantages and disadvantages, which I'm not going to discuss in detail about what are the strengths and the weaknesses, as I said, about the nuclear or the hydroelectric power, because nuclear energy has its own downsides based on how are you going to if something, as we know, the classic case of Japan, like what happened there, and it is very difficult to control at some point of time, like what would be these radiative waste coming out of the nuclear centers. So, but at the same time, you will have real good energy with relatively cheaper price. But at the same time, if you come to hydroelectric power, we need this natural water flow kind of thing. And if it is also will be restricted to given these things. Of course, as I said, everything will have its own advantages and disadvantages. But my expertise and the background that I come from, it makes sense for me to talk about the solar energy rather than the nuclear energy or the hydropower, these things. Coming to the solar energy, the radiance, the energy that we receive from the sun has powered life on Earth for many million years. And I don't want to get into details, as like the thermonuclear fission reactions occurring in the sun are responsible for these radiations. And it have a pretty 3.86 into 10 power 20 megawatts per second is the output that the sun would emit from as part of the radiations. As you know, the electromagnetic radiations will have different components like gamma rays, X-rays, ultraviolet, visible, infrared, microwave, and radio waves. And most probably in the next 20 minutes of my talk, I will be talking in detail about the visible aspect of it and how to convert this visible light to energy and how solar cells would help you in doing it. So before getting into the solar cell aspect of it, what is important, what is important for you to understand is this one. So what is called as air mass. Air mass is when the radiations comes from the sun and reaches to the earth, it has to go to different layers, because air mass is nothing but the mass of the air, which is proportional, which is dependent on the temperature and the pressure in the atmospheres or the surroundings. So when it travels from earth and you have these different surfaces, different atmosphere, I mean different at different heights, you'll have different heights, different air mass available. Because of that air mass, you'll have a different amount of scattered light. You will have a different way of the light which propagates to this. So what is when you are fabricating any devices like solar cells or anything, so there should be a given standard, so that whatever the device that you fabricated in your laboratory, being sitting in India, should be the same if somebody replicates your process sitting in some North America or Europe. So for that, we need to have some laboratory conditions where we talk about under given conditions, if we test our device, which is called laboratory, for that we typically test our devices at AM 1.5, which means that it has an angle of 48.2 degrees centigrade, and whatever, when it reaches to this, in this particular context, all device would be fabricated, would be measured. So under the simulated conditions, what we call as solar simulator, under the simulated conditions, you will have a device performance comparable or will be similar. Doesn't matter whether the device has been fabricated and tested in any part of the world. So understanding the radiation part and getting the solar simulated radiations is critical. So now, if you see, you will have, whenever you have this incoming solar radiations, you will have a lot of scattered light, reflected light, and some of the components only reaches that. As I said, I'm not going to discuss again in these aspects, but there will be a lot of losses coming from the during the light traveling from the sun to the Earth's surface, which needs to be considered. And then you have a spectral or a solar spectrum at different radiations, which is AM 1.5 as shown in here. So now coming to the background of the solar cells, it's the first in 1839, the French physicist Becquerel first recognized the photovoltaic effect, which is nothing but generating the voltage using it's what photovoltaic effect. So later that has been used for fabricating various devices. So in the sequential order, in 1883, the first solar cell was built by Charles Fritz, who coated semiconductor selenium with an extremely thin layer of gold to form the junctions. But in 1954, the Bell Laboratories, which is found accidentally, they found that the device could convert around a 6% efficiency, which is, they are working with semiconductors, and they found that upon doping of the silicon with some impurities, they are really sensitive to light. And then when they measured, they could found that the sunlight conversion efficiency is around 6%, where we'll talk about what is that 6% kind of a thing. And later, there's initially the usage of these things, because of so expensive in nature, they were restricted their applications only for the spacecraft, for solar panels, when they were using this US satellite Vanguard 1. Now, to understand the solar cells or any of these devices, what is important is to understand the electronic structure, which I said in the beginning. If you take a single atom, and then if you take 2 atoms, and if you take 10 atoms, and if you take n atoms. So if you see here, this is how, if you are increasing the number of atoms, what happens to the crystal structure, or what happens to the band structure or the electronic structure. Usually when you're talking about only if you're still in the number of atoms, if they're not huge number of n number of atoms, means you're talking about n over the number of atoms. If you're only having less than that, you still talk about from an orbital's perspective. But if you have more and more orbitals, more and more atoms, the orbitals which are coming from these atoms would form a solid, because it will be so difficult to differentiate them. So now if you take an atom and if you bring 2 atoms, as you know that you will have a bond formation, right? So the bond formation will be having a regular things like linear combination of atomic orbitals, or the molecular orbitals, which you have studied in your +1 and +2, where we will be talking about valence, where you will be talking about highest occupied molecular orbitals and the lowest unoccupied molecular orbitals, which is a simple thing. Like you take one orbital here, another orbital here, you combine them, and you will have an hybrid orbitals, which is called in hybridization theory, where you will have the molecular orbitals with the low energy and the higher energy, and the electrons which are available with the lower orbitals can be filled here, and the energy with the orbitals at the pi star or the sigma star would be usually unfilled, or it depends on the electrons which are available, it can also be filled. So, but what happens if you keep on increasing the number of atoms? It means what happens is you have 2 atoms, and if you have 4 atoms to 10 atoms, then the corresponding molecular orbitals increases and the gap between them decreases. In that case, if you have series of Avogadro number of atoms, the distance, the levels which are between them, the discrete levels, will become continuous levels, and thus you become a solid. So where you are talking from a molecule structure, from a molecule where you have an this one, where then it will finally convert into a solid. So now when you have this solid, you will have the filled orbital, a filled solid, which is called valence band and the conduction band. So now, basing on the electronic structure, one could define the valence band and the conduction band. And now you are talking about the molecules in one state and the atoms and so these things. But if you take the nano, which is having limited number of atoms, we still have a discrete number of levels. Because of that, you will find unique quantum unique quantum information available, where you can talk about the quantum states and resulting from the density of states coming from the whether you are talking about 1-dimensional, 2-dimensional, 3-dimensional solids. Now, coming to the regular band structure, where you are talking about the valence band and the conduction band. So maybe I'll just, so what happens is, in the case of semiconductors, you will have, as you know, you will have 3 different materials. Any of the material that you take, you can classify them as conductors, semiconductors, and insulators. In the case of conductors, there will be a overlap between the conduction band and the valence band, which we call them as metals. And then coming to the semiconductors, you will have some band gap between the valence band and the conduction band. But if the band gap is more, I mean, instead of 1 electron volt, if the gap is more, if it is around anything more than 4 or 5 electron volts, then it is called an insulator. The reason is, doesn't matter. See, you have all your filled electrons in your valence band. So if you get conductivity, if you can excite them by various means, either through light, by applied potentials or whatever, if you can transit them to the conduction band, then you will have the probability of the electrons being moved in the conduction band, and then you can use as semiconductors. But beyond the level, then it will become difficult for an what you call the additional forces like the light or this voltage to make your electrons shift from valence band to the conduction band, and thus it becomes insulating. So now our interest is to look into the zone where we're talking about the semiconductors. So now coming to the semiconductors, you need to know there are 2 components, 2 types of semiconductors. One is the direct bandgap semiconductor, other one is the indirect bandgap semiconductor. In the case of direct bandgap semiconductor, where you have the minimum of the valence band and the maximum of the conduction band, valence band and the minimum of the conduction band have the same symmetry. It means that if I excite my electron from here to here, as they don't really have any difference with respect to momentum, so you can have this excitation possible, and then you can come back, the recombination is also possible. So when you have a direct bandgap semiconductor, which will be really good for optoelectronic devices, but when you have an indirect bandgap semiconductor, the maxima and the minima are not having the same momentum. It means that what it means is it has to undergo a transition, or it has to go it has to go for a different K value for getting it back to a transition to an for the transition to complete. So these are all called as indirect bandgap semiconductors. So now with these things, we'll come to the silicon. As again, you might have known about the silicon is a 4th group element with 4 electrons in the valence shell. And if you take a silicon, all the 4 electrons of the silicon with another 4 electrons of the another silicon will bond together, forms a covalent bond, forms a silicon with a tetrahedron geometry. Now, if you see this, there are no free electrons available. Whatever the electrons which are available here are already bonded. So then it means that as such silicon cannot be used for any electronic application because there are no free electrons available for the system to utilize for your purpose. So for that reason, most of the semiconductors, if you have what we call them as intrinsic semiconductors, where you don't really have the ability to conduct the electrons to go from an excited to the ground state, as they not have the free electrons. But at the same time, what we call them as intrinsic semiconductors, which is said. Then when we have something called an extrinsic semiconductors, in the case of extrinsic semiconductors, what you will do is you will replace the silicon with either boron, either one of those electrons, atoms with having low number of, less than 4 electrons or more than 4 electrons. So that's what we call them as N-type doping or a P-type doping. In the case of P-type doping, what you do is what you will end up with, where you will have an excess, where you have a hole where it is not filled with. So though the boron, because of this one. And in the case of N-type doping, you have 5 electrons coming from the 5th group. So what will happen is you have an excess electron. So because of this, your valence band and conduction band will move in the case of P doping and the N doping. In the case of P doping, your Fermi level would be close to valence band. In the case of N doping, your Fermi level would be close to conduction band because of the excess electrons available. So because of these things, they will be able to have the charge carriers for your charge carriers which are required for any device fabrication. Now, when you take a P-type material and an N-type material, as you know, they will be forming a PN junction. When you have this PN junction, you will have either you can connect the PN junction, which means P-typed and P-doped and N-doped. And when you put them together and you apply the bias, you can have 2 different conditions. One is called a reverse bias condition or a forward bias condition. Only in the case of forward bias, you will see upon increasing the voltage, the current increases because of the combination, how the charge carriers can flow in when you have PN junction this. But in the case of reverse bias, the depletion layer will become so high, it will become so big that the voltage that you apply will become difficult to generate the charge carriers to move from one direction to another direction. After a certain time, if you can see in the reverse bias direction, you're not able to see any current because there are not really any charge carriers flowing from one to another, from one terminal to another terminal. But if you, beyond a point, if you want to increase this, as you know, there will be a breakdown voltage where we call it as an avalanche effect, where you will see, where you will clearly see the device would not work any further because of this breakdown of this device. But in the case of forward bias, you will have the current coming up with the increase in the voltage, which means that there are some charge carriers traveling from one direction to another direction. And because using this phenomena, one could fabricate transistors, solar cells, LEDs, photodetectors, and diode lasers. So I'll be discussing about each of these things in detail to some extent. And now coming to the other aspect of it is the basics of the solar cell. When you are talking about the solar cells, how do we characterize them? So there are 3 different parameters which are critical to calculate, evaluate the device performance. One is called open circuit voltage, other one is called short circuit voltage, other one is the fill factor. And combination of these things, you will get a power conversion efficiency, which essentially tells you how efficiently you are able to convert the light into electricity. This is exactly the power conversion efficiency is all about. So what is open circuit voltage? If you bring 2 different materials together, there will be some difference in basing on the electronic structure. There will be, you take between a metal semiconductor or a semiconductor interface, there will be a voltage gap. There will be some voltage difference would be there because of the difference in the Fermi level of the system. So because of that, you will get an open circuit voltage. And the short circuit current is the current at which at the 0 voltage, the maximum current that a device can get. And the fill factors is the place where you will get the maximum power conversion efficiency. As you know, we calculate the power as a function, as the multiplication of the voltage and the current density. So you see, when you're measuring, when you're fabricating the device, you could operate the device at any potential. Like either you can operate the device at open circuit voltage, or you can operate your device at the short or zero voltage, which means that at the short circuit current conditions. But for getting the maximum voltage, you want to have both short circuit current as well as the voltage. So this is the point where you will have the power conversion efficiency maximum. And how do you define that? The power conversion efficiency maximum is P0 by P0, which is like multiplication of JSC into VOC into fill factors by P0, which is nothing but the average, the initial or the incident power, which we are shining this here. And now, coming to the fundamentals of how understanding these solar cells would, how these solar cells would work. So what happens is you'll have different, when you are talking about solar cells, you need to understand that you are talking about how you have, what is the incident light and how many of these photons are able to convert effectively to charge carriers for giving you the electricity or the current. Right. So now you have different losses, which are called thermalization losses, junction losses, contact losses, and the recombination losses, which I'm not going to discuss any of these things. But essentially what happens is you need to understand what happens when you shine the light on your device, what happens, how the light interacts with your device, and how it converts the incident light into electron hole pair, and how it enables your device to function. So now this is how various losses are there, but now we'll be discussing about various silicon solar cells. I'm sorry because I'm not getting any details because of the interest of time, but I'll be more happy to discuss with one-to-one on these aspects, like how these devices works and how one would look into these things. So coming to the new generation solar cells, there are silicon solar cells, dye-sensitized solar cells, hybrid inorganic, organic solar cells, and organic solar cells. Coming to the first part, where you are already seeing them into the market, where to a major extent the technology has been matured and you are using it in household activities as well. But of course, they're relatively expensive, and of course, there are efforts are being drawn in the direction, though the price has reduced significantly compared to 20-30 years before, but still people are trying to reduce the price further so that it will become a household device. And the other three are still in the research level, and some of them are commercialized to some extent, but not the way the silicon solar cells are commercialized. So in case of silicon solar cells, there are two to three different silicon varieties are there. One is monocrystalline solar cells, other one is a polycrystalline one, other one is amorphous. What it means is whether you take a monocrystalline or a polycrystalline or amorphous, the conductivity of these devices would vary. Because of the monocrystalline will have really conducting, because of the pure silicon, you will get the you'll get band-like transport. In the case of polycrystalline silicon samples, because of the defects and the polycrystalline in nature, the conductivity of these systems would not be as good as the monocrystalline. So there will be some compromise with respect to efficiency. In compared to the amorphous silicon, it is the advantage of the amorphous silicon is you can fabricate them on a flexible device, but what happens is because these are amorphous, the conductivity of this device would decrease, and then if you have low conductivity, the recombinations would be high, thus decreasing the efficiency of your device. So now if I have to put it in a very simple terms on how a photovoltaic device would work, you have a valence band and the conduction band of two different materials, and then when you excite the light, your charge carriers from the valence band goes to the conduction band, and from the conduction band, because of the potential gradient that it is there, because of the p-n junctions, there will be corresponding the difference in the Fermi levels, there will be the electrons transport from one side to another, and then you will fill from there, you will have the charge collection. From after that, when the p-n junction is connected with the external circuit, the current flows. This is how exactly what happens. So now what you're doing is you're shining the light, you're generating the charge carriers, and then after the charge carriers will move from one stage or from one system or one type of material to another material. After that, under external conditions, you will be able to power your device. This is how a solar cell works. And now coming to the fabrication process on how these solar cells are what you're seeing in the market are fabricated using this process. Like if you take the smaller one, we call them as a solar cell, where if you take the module, you have a series of cells connected, and then you have as many modules are possible, where we call them as arrays. So all of them are scalable in bulk scale. That's the reason you're able to integrate into various devices, and large area fabrication is possible as far as silicon is concerned. So now you take the raw material silica, which is nothing but sand. You do the purification process, and then you make the purification process involves converting from SiO2 to silicon, and then the crystallization and ignite production, and then wafer slicing. So this itself is a critical technology, and hopefully India will be in a position to get these things. As of now, we are not doing much into this area, even from a manufacturing perspective, but of course we are doing a lot on assembly perspective kind of a thing. But producing the silicons itself is then really technological relevant with the new schemes announced by the government. So we may be in a position to do these things in a better way. Of course, these are all the technologies which are completely mature. So once you make your silicon with the highest purity possible, like 99.99%, then you have to go for wafers. Followed by soda damage removal, surface texturing, diffusion. So, and then you have to have another various levels, and after that you'll have an anti-reflective coatings, and then you have to go for final cell fabrication. So this is how amorphous process would look like, which I'm not getting into detail, but this is how, because as I said, these are flexible in nature. The other one is in dye-sensitized solar cells, which is of recent discovery, where Professor Grenzel, who is shown, who is the inventor or who discovered this system, where essentially we're using the dye for harvesting. Essentially what we're talking about is how many photons that you can absorb in your system, because we are talking about your light converting into electricity, right? If you can absorb more and more light, it will be better. You'll have the probability of you getting the higher efficiencies devices are high. So for that reason, you will in this concept, they use the conventionally used dye itself for sensitizing the light. So it means that the key component for absorbing the light is the for working your for effectively working your device is that how well you absorb your light. If you can use a dyes like the one which we color our homes with paints, so that they're having a significant color, right? It means that they have the ability to absorb the light in that the absorption or the emission corresponding to the band gaps, right? So in a similar way, if you have a material which can absorb more and more light, it will be always better. So they are utilizing the modifying the solar cells with a dye, and then they use this TiO2 and then the counter electrode with an electrolyte for coupling. Of course, there are people who, instead of using iodine iodide as an counter electrolyte, people have used even many other materials instead of using electrolyte. So this is essentially to fill the idea is to shine the light, generate your exciton hole, electron hole pair, and then transfer and then separate them and then collect them at the device. So by doing this, whatever is required, one need to do for fabricating the devices. So as I said, this is the summary of how it would work, where you have the charge separation from ground state to excited state, where you need a counter electrode to circle the loop. So now, instead of dyes, you can look into quantum dots, or you can use the perovskite-based solar cells, and of late, these of current research interest, where a lot of people are working in this, as the efficiency of the device are really high, where about 20-25%. So coming to the topic which I'll be discussing for the next 4-5 minutes is on the organic solar cells. As I said, whenever you have this device, you have these kind of components which are available. When you shine the light, you are creating the exciton. when you create the exciton, it goes, the second step is an exciton diffusion. When you go to the acceptor layer and then the diffused exciton, later you have to come for the dissociation. So when the exciton dissociates, you have your charge carriers, and then you have to have a charge collection using the electrodes. So with these things, where we will be talking about various components of organic solar cells. In this case, the specific aspect which I'm discussing with you today is on what we call them as fullerenes, where we are finding the alternatives to fullerenes because of them are expensive in nature. So there are various strategies which are reported in literature to make them suitable or make them solution possible. If you have to put it in one line, these are one of the cheapest solar cells that one could think of, because fullerenes which are used traditionally in organic solar cells are expensive. So now the idea is to reduce the cost of these things. So people are working on various aspects of different organic molecules to reduce the price instead of using fullerenes. So now here we are using a simple concept of slip stacking. If you take this one class of perlenes, which are nothing but the dye molecules which you use in variety of paint industries. As I said, it is important to have your molecule to absorb as much as amount of light possible. So now you have these perylene molecules with you, which are not really good conductors because of, not only that, at the same time, I mean, they're good conductors to some extent, but when you use them as such, they forms excimer because they have the pi-pi interactions. Because of that, you will have really high crystallinity. If you have real good crystallinity, in terms of conductivity, it will be better, but in terms of solar cell fabrication, it will not be great, because if the solar cell works with the interface between donor and acceptors. So now if you see this one, there are various to reduce this effect, or to minimize the crystallization effect, we use the slip stacking effect and fabricate and synthesize 3 different molecules and derive the crystal structures, and have done the detailed characterization on the homo-lumo levels of it, and then where you can clearly see this is a traditionally used fullerenes, and the band gaps are matching, where I'm not going to detail how to determine these energy levels. Otherwise, it would be nice to know how to derive the energy levels, the homo-lumo from the cyclic voltammetry. After that, we fabricated various devices, and then the efficiency of them are around 3.67%. As I said, though the efficiencies are not high, as these are really materials are really cheap. So for getting these efficiencies, one need to optimize various parameters like donor acceptors, different solvents, annealing, thermal annealing, interfacial layers. So then you'll end up with one good optimized structure to fabricate these solar cells. Once you fabricate the solar cells among these 3 molecules, which is synthesized, the phenyl PDI, the chain with length with phenyl group is for performing better, and we wanted to know why this phenyl PDI is doing better. So now when you're doing this phenyl PDI, we did this device efficiency at different thickness, and then we found that at a given optimum thickness of 60 nanometers, it works better. Even if you have low thickness, it is not good. If you have more thickness, it's not good, because you have competing interests coming from the absorption with the charge transport. After that, we have to understand how these devices are working. We fabricate the thin film transistors, and we found that the guy who is working better are having having high electron mobilities compared to the other 2 systems. So helping you thinking that why your device are working for a one given system compared to other things. So the nano component of this is, as I said, when you have this donor and acceptor interface, if you mix them together and if the interface is good, then only you'll be able to fabricate device of good quality. So from the AFM image also, we found that if you take one of those things like XLPDI, you see the crystallines are so large in nature, but when you come to the phenyl PDI, so you have an optimum amount of donor acceptor interface. And the same thing has been confirmed again using the GWAX, which is glazing instance wide angle X-ray scattering, essentially tells you about the crystallinity. What is important for organic solars to work is the interface, which means coming or the domains forming between the donor and acceptor interface, where you can clearly see here, and the crystallinity aspect of it. If you have more crystalline also, it is not good. If you have less crystalline also, it is not good. What we found is the crystallinity, which is intermediate between them, is really important for fabricating really high efficient devices. And then we have added some meditools to control the interface as well as the crystallinity aspect of it by adding diiodo-octane, which is having its impact, and we found that the optimum amount of diiodo-octane is critical for having high efficiency devices. And as I said, what is also important is, in our case, the quenching efficiencies are about 90%. It means that the exciton travels to the interface and get into charge transfer state. It means that we are not limited by the charge transfer, but we are limited probably by the transport, which is understandable because of the nature of the organic molecules that we work with. And then we did a detailed studies on charge separation aspect. What we are talking about here is the when you are shining the light, the number of electrons and holes that you could create by shining the light. This essentially, this data would suggest you that if you see this device, that the phenyl PDI has the ability to convert more than 50% of your device to a charge separated systems compared to other things. And that it again supports your argument that phenyl PDI is working better compared to other systems. So with these things, what I would like to conclude is that when you want to fabricate any organic solar cells, what is important is to understand the nano aspects of it, like how the organic donor acceptor interface is, how the crystallinity is, and how the transient absorption spectroscopy works out in terms of the duration of the charge species will help you to get, if the charge species lives for longer duration, the probability of separating them would be high. Otherwise, if they recombine at the early stage, you will not able to separate the electrons and hole, because the whole idea of solar cells is to separate the electron and hole being generated upon shining the light. So all these parameters would help you to fabricating high efficiency devices. With this, I would like to conclude and will be happy to take any questions.
Thank you, Ramakrishna Matte sir. I would like to request the audience, if they have any queries, the session is open for discussion here. Indeed, it was a wonderful session by Matte sir. I would like to thank him for engaging such a wonderful session. Now I request our head School of Physical Sciences, Dr. P.R. Jirgal sir, to propose his vote of thanks.
Good afternoon to all the delegates and resource persons. I, Dr. P.R. Jirgal, head of the Department of School of Physical Sciences, would like to propose vote of thanks. My heartfelt thanks on behalf of faculty, that the principal and the student fraternity, that is to Royal Society of Chemistry, Deccan, that is for all the assistants to conduct this valuable, that is a fruitful seminar on functional, nano and soft materials, fundamental and applications. My special thanks to the resource persons and eminent scientists. That is firstly, that is Professor B.L.V. Prasad, Director, Center for Nano and Soft Material Science, Bangalore. That is for his valuable and fruitful and there is a title. There is a nanoparticle synthesis, surface modification and applications. There is a, I'm very thankful to you, sir, for your eminent speak. And secondly, I'm going to
there is still my special thanks to there is the under resource persons and there is the eminent speaker, there is a scientist, Dr. HSS Ramakrishna Matte, who spoke on there is the new and big science of a small. Thank you, sir. Thank you for your very eminent there is the talk, sir. There is the thirdly, there is the, I'm going to extend my there is the thanks to there is the Dr. CV, there is the El Magat, a scientist and eminent speaker, there is the who spoke on there is the fundamentals and applications. There is the fascinating matter. There is the fundamentals and applications, and I'm very thankful to you, sir. There is the I'm very thankful to all the team of Center of Nano and Soft Material Science. There is a like Pinto Ganguly sir and all the team. There is for their active, there is the participation and there is the assistance in all the aspects, sir. And I'm very thankful to all. There is I'm very thankful to my there is a principal of my college. There is who has assisted in all the respect to carry out there is to conduct this seminar effectively. And I'm very thankful to all my there is a faculty of School of Physical Sciences. There is for their assistance in conducting this seminar effectively. And my special thanks to all the delegates that we have taken the part in this the seminar and made use of. And I'm very thankful to you, sir. There is all the eminent speakers and scientists. There is who have given their valuable talks. There is all the 3 sessions with your valuable talks, and all the delegates. According to me, they have benefited a lot. I'm very, very thankful to you, sir, once again, to all the team of what now Center of Nano and Soft Matter, there is the Sciences, sir, Bengaluru. Thank you, sir. Thank you, one and all.
Thank you, sir. Now, Ganguly, sir, I would like to thank you once again for being there with us throughout the entire seminar. And I thank all the participants.
Also on behalf of RSC to the management, principal, and every one of you for having us associated with and having this wonderful session. Thank you all.
Thank you so much for letting us have an association with you, sir.
Thank you.
Yes, thank you so much, all the participants. The feedback forms will be sent through the Telegram group, which has been created for the purpose of this seminar. I request all of you to give your valuable feedback in the form, and you'll receive the participation certificates as soon as you submit the feedback form. Thank you.